Imagine floating through a cosmos teeming with vibrant spirals, galaxies ablaze with star formation, their arms glowing blue with newborn suns. Among them lies something different. Still spiral-shaped, yes. Still majestic in form. But it lacks the shimmer, the chaos, the life. It's pale. Faint. It feels like a memory more than a structure. You've just found an anemic galaxy, a ghostly spiral drifting quietly through space, no longer thriving, but not quite gone. But before we continue, subscribe to the channel so you don't miss out on any of these videos. In the grand theater of the universe, where galaxies spin, collide, and give birth to countless stars, anemic galaxies are the subdued performers. They don't shine with the blinding intensity of starburst galaxies. They don't rage with the fury of galactic mergers. Instead, they persist in a curious silence, like music turned to a whisper. The term, anemic, couldn't be more appropriate. Just as an anemic human suffers from a deficiency in vital nutrients, particularly oxygen-carrying blood, an anemic galaxy suffers from a deficiency of the fuel that makes stars, cold gas, especially neutral hydrogen. But what makes this galaxy so different? At first glance, it may not be obvious. Many anemic galaxies maintain the broad structure of a spiral, a central bulge surrounded by swirling arms. But the spiral arms are subdued, poorly defined, like a pencil sketch rather than a vibrant painting. These arms are not bursting with clusters of young, hot, blue stars. There are no dense knots of bright nebulae where stars are forming. The colors lean toward red and yellow, signs of older stars, long past their youth. Anemic galaxies are not failures. They are not malformed. They are transitional. They are the in-betweeners of the galactic zoo. Not quite living in the way we define active galaxies, and not yet dead like fully quiescent ellipticals. They occupy a space that's more philosophical than observational. They are galaxies caught in a slow transformation, fading ever so gently, slipping toward dormancy. In a universe governed by extremes, brilliant supernovae, roaring black holes, rapid starbursts, anemic galaxies offer a more subtle story. They tell of slow processes, of galaxies being quietly stripped of their fuel, of changes so gradual they go unnoticed for billions of years. They are what happens when a galaxy loses not through destruction, but through erosion. They are what happens when a galaxy gets tired. And they matter. They matter because they give us a window into galactic aging. They are not rare flukes. They are waypoints on the journey of galaxy evolution. Studying them reveals how galaxies fade, how they transition, how environmental forces and internal dynamics conspire to silence once lively systems. So when we speak of anemic galaxies, we're not talking about curiosities. We're talking about a natural stage, perhaps even a universal one. Could the Milky Way, in its distant future, one day wear this pale, faded face? Could our descendants look up at a dimmer sky, not because the stars are gone, but because the galaxy itself has lost its will to make more? Anemic galaxies raise profound questions. What quieted them? Will they ever reignite? Are they simply waiting for a chance to live again, or are they the harbingers of galactic old age, the last, dim chapters of a story that once burned bright? This video is their story. A tale of faded spirals. Of starbirths slowed to a crawl. Of gas stolen and never returned. Of cosmic winters, and the galaxies that endure them. To understand where the term, anemic galaxy, came from, we have to step back into the 1970s, a time when the classification of galaxies was becoming more nuanced, and astronomers were refining the way they described the universe's grandest structures. Among them was Alan Sandage, a protege of Edwin Hubble and a giant in his own right. Sandage wasn't content with simply slotting galaxies into the traditional Hubble tuning fork of spirals, ellipticals, and lenticulars. He observed something peculiar, a subset of spiral galaxies that just didn't fit. They had the same disk shape, the same central bulges, and even the familiar spiral arm layout. But they looked off. Their arms were faint, poorly defined, and lacked the blue clumps of newborn stars typical of vibrant spirals. These galaxies didn't seem dead like ellipticals, but they certainly weren't alive with activity. They were pale, faded, dim. In 1976, Sandage formally introduced the term anemic galaxies to describe these objects, spiral galaxies that appeared to be running on fumes. The metaphor was as much poetic as it was scientific. Just like a person suffering from anemia is low on red blood cells and thus weak and tired, these galaxies were low on the cold gas necessary for star formation, making them appear weak in a cosmic sense. It was a groundbreaking insight, suggesting that galaxies could exist in a kind of semi-dormant state, not dead, but definitely not thriving. What made the idea so revolutionary was that it challenged the binary thinking of the time. Until then, galaxies were often viewed as either active, forming stars, or passive, not forming stars. But anemic galaxies existed in the twilight zone in between. Sandage's naming helped crystallize this concept, offering a linguistic and conceptual bridge between the categories. His work also hinted at an important realization: galaxy morphology wasn't just about structure, it was about behavior. A galaxy might look like a spiral, but if it wasn't acting like one, if it wasn't forming stars, if its arms were ghosts rather than engines of creation, then it belonged in a different category. The term, anemic, didn't just describe appearance. It described a state of being. Over time, the term caught on. Astronomers began identifying anemic spirals in nearby clusters and cataloging their properties. Sandage's simple but evocative phrase helped launch a broader discussion about galaxy evolution, about how galaxies transition from one state to another, sometimes slowly, almost imperceptibly. In a sense, naming something gives it power. It grants it identity and invites inquiry. By calling these galaxies anemic, Sandage didn't just describe them, he gave astronomers a new question to ask: what causes this anemia? Is it environmental? Internal? Reversible? Or is it a terminal decline? That question would set the stage for decades of research, and anemic galaxies would become key to understanding one of the most important processes in the cosmos: the quiet quenching of galactic life. The quiet tragedy of anemic galaxies lies in their most telling trait: their star birth has nearly come to a halt. In most spirals, the arms are bustling with brilliant, blue, short-lived stars, the unmistakable sign of recent and ongoing stellar formation. These stars burn hot and fast, lighting up the dusty nebulae from which they were born. But in anemic galaxies, this activity is subdued, almost eerily so. Star formation still occurs, but at such a slow, diminished rate that it barely registers compared to their more active counterparts. What we see instead is a galaxy coasting on momentum. The older stars remain, aging into yellower hues, their energy output cooling with time. But the young ones, the wild, radiant infants of the galactic nursery, are few and far between. It's not that these galaxies are incapable of forming stars, it's that they've nearly lost the capacity. The interstellar medium, the raw material needed to make stars, is thin, depleted, or disturbed. As a result, the engine of star formation sputters along rather than roaring to life. In typical spiral galaxies, particularly those in the so-called main sequence of star-forming systems, there's a direct link between available gas and star formation rates. The denser the cold gas, the more vigorously stars are born. In anemics, this relationship is broken, or at least weakened. The spiral structure is there, suggesting that the galaxy should be alive with new stars, but it's as if the lights have dimmed, the orchestra has gone quiet, and the stage is nearly empty. The signature blue of massive, young stars is largely absent in these galaxies. Instead, their spectral energy distributions lean toward the red and infrared, dominated by older stellar populations. Ultraviolet emissions, often a proxy for recent star formation, are extremely faint. These galaxies are not bursting with HI regions, those glowing clouds of ionized hydrogen that mark active star-forming zones. Instead, any such regions are small, scattered, and weak. Observations using instruments like the Hubble Space Telescope and GALEX, the Galaxy Evolution Explorer, have confirmed this decline. GALEX, which specifically observed in the ultraviolet spectrum, revealed that many galaxies categorized as anemic had UV emissions so low that they were barely distinguishable from quiescent galaxies. Yet structurally, they still resembled spirals, a contradiction that continues to intrigue researchers. This slow-motion star birth also affects the overall evolution of the galaxy. Without new stars to stir the galactic pot, injecting energy into the interstellar medium through stellar winds and supernova explosions, the galaxy becomes more stable, even stagnant. Dust settles. Turbulence fades. The arms remain, but they lose definition, and the color palette shifts from vibrant to muted. Over time, the entire system grows quieter and redder, like a fire slowly burning out. It's a cosmic deceleration. Anemic galaxies aren't collapsing, exploding, or colliding. They're simply fading, retreating from the energetic process that defines so much of a galaxy's identity. It's a slow death, if you can call it that, more like a long slumber, where star birth never truly stops, but trickles down to a pace so slow it could be mistaken for stillness. In this gentle, creeping silence, we find the essence of galactic anemia. Not a catastrophe, but a suffocation of potential. A star factory that still spins, but barely operates. And in that, a mirror perhaps, of systems in transition, not just in space, but in every corner of nature where energy gives way to entropy, and light gives way to dusk. In the glowing spirals of typical galaxies, the arms are bold and luminous, clear lanes of gas and stars coiled like cosmic pinwheels. These arms are more than just visually stunning, they are the bustling avenues where star formation thrives. Dense waves of gas compress the interstellar medium, triggering bursts of stellar birth that illuminate the structure and carve out sharp, beautiful patterns. But in anemic galaxies, those same arms take on a ghostly appearance, present in shape, yet drained of definition. They spiral not in glory, but in shadow. The spiral arms in anemic galaxies seem like the fossilized remnants of past vitality. They're still there, coiling outward from the central bulge, obeying the same dynamics that shaped them billions of years ago. But their brightness has faded. The usual highlights, young, hot stars and glowing gas clouds, are missing. Instead, the arms look smooth, almost featureless, populated mostly by older, redder stars. It's as though the structural blueprint remains, but the substance that gave it life has eroded away. Astronomers have studied these faint arms in detail using both optical and infrared imaging. In visible light, the contrast between the spiral arms and the disk is barely noticeable. They blur into the background, lacking the crispness found in more active spirals. In infrared, which traces older stars, the arms are still discernible, suggesting that the stellar skeleton is intact. But the youth, the bright, star-forming spark, is gone. This raises fascinating questions. How do spiral arms persist in galaxies that have long stopped forming stars? After all, spiral arms are typically thought to be density waves, regions of enhanced gravity that sweep through the disk, compressing gas and igniting star formation. In anemic galaxies, the density wave may still be present, but without gas to compress, there's nothing to ignite. The wave moves through a depleted medium, stirring dust that no longer dances. Some researchers suggest that the spiral arms in anemic galaxies are relics, long-lived features left behind after star formation was quenched. Without the turbulent forces of stellar feedback or supernovae to disrupt them, these arms become stable, smooth, and uneventful. Others propose that the arms are slowly unwinding, fading not just in brightness but in structure as the galaxy drifts toward a lenticular or elliptical state. Simulations support this view. When a spiral galaxy is stripped of its gas, whether by environmental forces or internal exhaustion, the spiral arms begin to lose their sharpness. They don't vanish instantly, but gradually fade over time. The stars that once traced bright, blue arcs remain in orbit, but their arrangement becomes diffuse. What was once a vivid swirl becomes a soft haze. There's a poetic sadness in this image, galaxies still spinning in beautiful form, but with no spark left to animate their curves. It's like a carousel in motion long after the music has stopped. The movement remains, but the joy is gone. Even in this quiet decay, however, there is information. The shape of the arms, their pitch angle, their coherence, all of these features tell astronomers about the galaxy's history. They are clues to a past filled with light, and to a transformation now well underway. Faint spiral arms aren't just aesthetic curiosities. They are the fingerprints of what once was, ghosts of a starry past, etched across the face of galaxies that no longer burn with youthful fire. The fading brilliance of anemic galaxies can often be traced back to a single missing ingredient, neutral hydrogen, or Hi. This cold, simple atom is the raw fuel from which stars are born. Without it, the entire star-making machinery of a galaxy grinds to a halt. And in anemic galaxies, that fuel tank is astonishingly empty. Neutral hydrogen is typically abundant in healthy spiral galaxies. It exists in vast clouds that drift between stars, invisible to optical telescopes but glowing faintly at a specific radio frequency, the famous 21 centimeter line. This emission allows astronomers to map the presence of hydrogen across galaxies, even when no stars are forming. When a galaxy is full of Hi, it's like a factory stocked with raw materials. Star formation is active, self-sustaining, and efficient. But in anemic galaxies, Hi is scarce. Radio surveys such as those from the Arecibo Observatory and the Very Large Array have shown that these galaxies often have significantly reduced amounts of neutral hydrogen compared to typical spirals of similar size and mass. In some cases, the gas is not just reduced, it's almost completely absent. And this absence has profound consequences. Star formation begins when cold hydrogen clouds collapse under gravity, forming dense molecular clouds that eventually give birth to stars. Without a robust supply of Hi, this process is severely limited. It's not just that the galaxy isn't forming stars now, it can't. The well has run dry. The depletion of hydrogen affects everything else. Without young stars, there's no ultraviolet radiation to ionize gas and create glowing nebulae. Without massive stellar winds and supernovae, there's no turbulence to stir the interstellar medium. Without dust heated by newborn stars, even infrared signatures become faint. The entire ecosystem of a star-forming galaxy collapses inward, like a city where no new citizens are born and the infrastructure slowly decays. There are many possible reasons why this hydrogen goes missing. In many cases, environmental factors play a role. Nearby galaxies or the harsh environments of galaxy clusters can strip a galaxy of its gas. Other times, the galaxy simply consumes its gas supply over billions of years, and no new gas falls in to replace it. But whatever the cause, the result is always the same: star formation slows, then nearly ceases. In the most extreme cases, even the molecular hydrogen, H2, the more tightly bound and colder form of the element necessary for direct star formation, is gone. The anemic galaxy becomes not just a gas-poor system, but a gas-empty one. Its spiral arms may still exist, but they are no longer laced with the filaments of possibility. The future has been taken away. This loss is not always total, though. Some anemic galaxies retain thin traces of hydrogen, especially in their outer disks, where low-level star formation might persist at a snail's pace. And in rare instances, a fresh infusion of gas from a merger or intergalactic stream could potentially reignite a spark. But these are exceptions, not the rule. Most anemic galaxies have been fundamentally altered by the disappearance of their cold gas, and they wear that emptiness in every pale, faded feature. It's a sobering lesson in cosmic fragility. The universe may seem eternal and inexhaustible, but even grand spiral galaxies, rich with stars and motion, are vulnerable to starvation. And in anemic galaxies, we see the end result: spirals that still move, still spin, still hold their shape, but no longer have the breath to speak in starlight. The more we study anemic galaxies, the more we realize they exist in a peculiar in-between space, not fully spiral, not quite lenticular. They blur the traditional lines astronomers have used to classify galaxies for nearly a century, making us rethink how rigid or fluid these categories really are. At a glance, they may still carry the familiar spiral shape, but upon closer inspection, their muted appearance, passive behavior, and lack of star formation push them toward a quieter identity. They exist in a state of galactic ambiguity, transitional and unresolved. Lenticular galaxies, known as S0 galaxies, are considered hybrids between ellipticals and spirals. Structurally, they resemble spirals. They have a central bulge and a flat disk. But unlike classic spirals, They lack prominent arms and have little or no ongoing star formation. Their stellar populations are dominated by older, redder stars, and their gas content is minimal. S0 galaxies are often thought of as faded spirals, galaxies that once had active arms but somehow lost the energy and material to sustain them. This is where anemic galaxies come into focus. They don't match the bold spiral category anymore, but they aren't fully S0s either. They still have spiral arms, albeit faint. They still possess some structure in the disk, some rotational dynamics, and occasionally even trace amounts of star-forming activity. Their disks aren't yet passive, but they are clearly in decline. They are, quite literally, spirals in the process of transformation, spirals on the road to becoming lenticulars. What's fascinating is that many astronomers now believe anemic galaxies may be the missing evolutionary link between vibrant spirals and passive S0s. They offer a snapshot of the transformation in progress. If galaxy evolution is a timeline, anemics are the midpoints, the transition phase that most galaxies must pass through if they are to lose their gas and spiral definition. The fact that they retain their disk shape and still show spiral features, though subdued, supports the idea that S0s didn't form from scratch, but from spiral ancestors that gradually wound down. Spectroscopic surveys lend more evidence to this theory. When we analyze the spectra of anemic galaxies, we find something curious. Their light profiles look more like those of S0s than of normal spirals. Their star populations skew older. Their emission lines, indicators of hot, young, star-forming regions, are weak or absent. Their rotational velocity curves, however, remain consistent with spiral dynamics, showing that they haven't yet collapsed into fully dispersion-dominated systems like ellipticals. It's not just a matter of morphology, it's a matter of behavior. Spirals are active ecosystems. Their arms are sites of constant motion, formation, and destruction. Lenticulars are quiet, settled structures. Anemic galaxies, meanwhile, are in flux. Their behavior reflects exhaustion. Their arms are still technically functional but largely inactive. The disk rotates, but without the vibrancy we associate with life. The system continues to spin, but its energy output has dimmed. This in-betweenness complicates classification. For decades, astronomers relied on the Hubble sequence, the so-called tuning fork diagram, to sort galaxies into discrete groups, ellipticals, spirals, lenticulars. But as more sensitive telescopes allowed us to see fainter structures, more subtle behaviors, and more transitional forms, it became clear that galaxy evolution is not as categorical as once thought. It's fluid, dynamic, continuous. Anemic galaxies are the embodiment of this continuum. They sit along the curve, not at its endpoints. There's also variation within the category of anemic galaxies. Some are just beginning to show signs of fading, their spiral arms are intact, and star formation is merely slowed, not stalled. Others are further along, their arms are barely visible, their disks are smooth and passive, and only the faintest traces of youth remain. This spectrum of decline suggests that the transition from spiral to lenticular is not a sharp break, but a gradual fading, like colors blending into one another on a cosmic palette. Environmental factors seem to play a strong role in this transformation, a point we'll explore in greater detail soon. But for now, it's important to understand that this blurring of lines is not random. It is patterned, predictable, repeatable. Many anemic galaxies are found in clusters, regions where gas stripping, tidal effects, and gravitational disturbances are more common. These forces don't destroy galaxies outright, they slowly reshape them. They rob them of gas, dull their arms, and reduce their ability to form stars. And over time, they move them along the evolutionary track from spiral to S0. Even in isolated environments, internal processes can mimic this journey. A galaxy might slowly use up its own gas over billions of years without replenishment. Star formation will taper off, spiral arms will fade, and the system will settle into a quieter state. The galaxy's structure may remain intact, but its behavior will begin to echo that of a lenticular. This dual identity, spiral in structure, lenticular in behavior, is what makes anemic galaxies so scientifically valuable. They are windows into a process that can be hard to catch in action because it occurs over vast stretches of time. In a way, observing anemic galaxies is like witnessing the leaves turning in autumn. You know the summer of vibrant star formation has passed, but the winter of complete quiescence hasn't yet arrived. The galaxy is caught in a slow transformation, one that will eventually reshape its identity entirely. And yet, anemic galaxies are not just a curiosity of classification. They are a crucial key to unlocking how the cosmic population of galaxies has changed over billions of years. Today, the universe is dominated by passive galaxies. But that wasn't always the case. In the early universe, most galaxies were actively forming stars. The presence of anemic galaxies shows us how that shift occurred, not through sudden, violent change, but through a gradual, persistent decline. The fading of a galaxy is not an event. It's a journey. And anemic galaxies walk the middle path. Their arms are still visible, though dim. Their disks still rotate, though quietly. Their stars still shine, though mostly in red and gold. They are not yet S0s, but they are no longer what they once were. In that liminal space, between motion and stillness, between growth and stagnation, lies the subtle truth of galactic evolution, that even the grandest systems, given enough time, slowly turn to silence. Anemic galaxies are not simply born faded, many are sculpted by their surroundings, transformed by the environments in which they dwell. And more often than not, that environment is a galaxy cluster, a cosmic city packed with hundreds or thousands of galaxies, where interactions are frequent and the intergalactic medium is thick with hot plasma. It's here, in these crowded neighborhoods, that the quiet death of a spiral galaxy often begins. When we examine where anemic galaxies are most commonly found, one trend is strikingly clear. They appear disproportionately in clusters, especially in their dense cores. Surveys of nearby clusters like Virgo and Coma reveal that many spiral galaxies in these environments are not forming stars at expected rates. Their colors are redder, their disks smoother, their arms faint, all classic signs of anemia. This suggests that the cluster itself is playing a significant role in draining these galaxies of their vitality. The mechanisms behind this transformation are subtle but powerful. Clusters are not just collections of galaxies. They are dynamic, violent ecosystems filled with searing gas, complex gravitational tides, and ceaseless motion. A galaxy falling into a cluster for the first time is not simply moving into a new neighborhood. It's entering an arena of forces that can shape its destiny. One of the most influential of these forces is ram pressure stripping, the interstellar equivalent of a headwind. As a galaxy moves through the hot, dense plasma that fills a cluster, the pressure from that gas can push against the galaxy's own interstellar medium. The faster the galaxy moves, and the denser the cluster's plasma, the more dramatic the effect. Eventually, this pressure can overcome the gravitational pull holding the gas in place, and the galaxy's cold hydrogen, the very fuel for star formation, is stripped away. What's left behind is a spiral structure with little or no gas, like a car with an empty fuel tank. The spiral arms remain, but they fade, deprived of their star-forming brilliance. This stripping doesn't happen uniformly. The outer regions of the galaxy, where gas is less tightly bound, are the first to suffer. Over time, the gas loss moves inward. In some galaxies, a faint ring of star formation might still cling to the outer disk, the last vestige of a fading process already well underway. In others, the gas is stripped almost completely, halting star formation across the entire disk. What remains is a galaxy that still looks like a spiral, but has lost the fire that once defined it. Yet ram pressure is only one part of the story. Clusters also bring galaxies into gravitational contact with one another, a phenomenon known as tidal harassment. These are not full-blown mergers, but rather glancing encounters, where galaxies tug on each other's stars and gas, subtly distorting shapes and stirring up internal dynamics. Over time, this repeated harassment can disrupt the spiral arms, heat the stellar disk, and drive gas inward or fling it outward. The result can be a disk galaxy that's morphologically perturbed and dynamically heated, and one that has lost a significant portion of its ability to form stars. Moreover, in clusters, galactic cannibalism is common. larger galaxies may absorb smaller companions, further disrupting their structure and sapping their gas. Even if an anemic galaxy avoids direct mergers, it might still experience satellite starvation, where its supply of fresh gas from smaller satellites is cut off due to environmental interference. Over time, the lack of external replenishment leaves the central galaxy to consume the last of its own gas reserves until there's nothing left to form new stars. The thermal environment of a cluster is another quiet killer. The high-temperature intracluster medium, often millions of degrees, prevents cold gas from easily condensing into the galaxy from outside. While isolated galaxies can slowly accrete fresh gas from their surroundings, cluster galaxies are immersed in a hot bath that actively inhibits such infall. It's like trying to collect rain in the middle of a desert. The potential for replenishment is blocked at the environmental level. All these mechanisms, ram pressure stripping, tidal harassment, satellite disruption, and hot halo quenching, work together to produce the same result: a spiral galaxy that is no longer what it used to be. Not through a single, catastrophic event, but through a prolonged environmental campaign. The cluster slowly, methodically strips its members of their ability to form stars, transforming the once vibrant spirals into pale echoes of their former selves. And the evidence for this process is not just theoretical. Observational data supports it with stunning clarity. In clusters, we see gradients in galaxy type: active, blue spirals on the outskirts; passive, redder anemics and S0s toward the center. This morphology density relation shows that the denser the environment, the more likely a galaxy is to be quenched. And anemic galaxies are the ones caught in the middle, closer to the center than the active spirals, but not yet as quenched as full lenticulars or ellipticals. Even more compelling are direct imaging results showing tails of stripped gas trailing behind galaxies as they move through the cluster medium. These gaseous streams, invisible in optical light but clear in radio and X-ray, are the fingerprints of ram pressure at work. Some galaxies are even caught in the act of being stripped, a rare glimpse into the moment a galaxy begins to fade. In this way, anemic galaxies become more than just passive objects. They are environmental artifacts, shaped by the massive, invisible forces of their surroundings. Their silence tells a story, not of failure, but of transformation through interaction. They show us that in the universe, context is everything. A galaxy's fate is not written only in its mass or its rotation speed, but in where it lives, what surrounds it, and how it moves through the gravitational and gaseous currents of the cosmos. They are the quiet casualties of crowded space, spun into shape by their own gravity, but silenced by the crowd they travel in. And in that silence, we find not just loss, but a kind of cosmic inevitability. Galaxies are not isolated islands. They are citizens of the universe, and like all citizens, they are shaped by the neighborhoods they call home. The transformation of spiral galaxies into anemic forms within clusters is not merely a result of long-term aging or passive internal decline. Often, it's a direct consequence of an invisible, yet immensely powerful force acting on them as they journey through dense cosmic environments, a process known as ram pressure stripping. This phenomenon can strip a galaxy of its star-forming material in a dramatic and nearly surgical fashion, reshaping its future in a single passage through the cluster core. To understand how spiral galaxies are drained and silenced, we need to dive into the mechanics of this powerful cluster wind. Picture a galaxy entering a galaxy cluster, an enormous, gravitationally bound collection of hundreds or thousands of galaxies immersed in a searing plasma called the intracluster medium, ICM. This medium, though extremely tenuous by earthly standards, is so hot it glows in X-rays, reaching temperatures of tens of millions of degrees. Galaxies entering this environment often travel at incredible speeds, sometimes up to 1,000 kilometers per second or more. And as they move, they experience the ICM not as a static field, but as a fierce headwind, like a car driving through a sandstorm. This is ram pressure, the same principle that pushes against your hand if you stick it out of a moving car window. In a galaxy, that wind is composed not of air, but of hot, ionized gas. As the galaxy pushes through this medium, its own gas, especially the loosely bound, cold hydrogen in its outer disk, feels the force of the wind. When that force exceeds the gravitational pull holding the gas to the galaxy, the gas is ripped away and trails behind like a comet's tail. The more massive the galaxy's speed and the denser the ICM, the stronger the stripping effect. The result is profound. A spiral galaxy that might once have been rich with gas, its arms dotted with bright nebulae, star clusters, and youthful blue stars, finds itself stripped bare. The neutral hydrogen, crucial for star formation, is the first to go. In more aggressive cases, even the denser molecular hydrogen clouds, the direct precursors to stars, can be affected, particularly in the outer regions. Without gas, the galaxy cannot replenish its stellar populations. It enters a phase of slow decline, and over time, the brilliant hues of youth are replaced with the steady, somber red of aging stars. Observational evidence for ram pressure stripping is abundant and striking. In deep radio surveys, galaxies undergoing active stripping show long HI tails trailing away from the disk, tracing the route of expelled gas. Some even have jellyfish morphologies, with wispy tendrils of stripped gas stretching back from the galaxy like stingers, indicating intense, ongoing interaction with the ICM. These tails can extend for tens of thousands of light years, sometimes longer than the galaxy itself, and are rich in clues about both the stripping process and the galaxy's motion through the cluster. One of the best studied examples of ram pressure stripping in action is the Virgo cluster, where many spiral galaxies display clear signs of gas loss. Galaxies like NGC 4522 and NGC 4402 have had their gas-rich outer disks stripped clean, even as their inner regions still cling to the last vestiges of star formation. In some cases, stars can even be seen forming within the tails of stripped gas, far from the parent galaxy, a testament to the resilience of gravity and cooling, even in the aftermath of such violent processes. What makes ram pressure stripping especially dramatic is its efficiency and speed. While many galactic evolutionary processes unfold over billions of years, ram pressure can significantly alter a galaxy in just a few 100 million years, a blink in cosmic time. A galaxy falling into the core of a massive cluster may be stripped of most of its gas after a single high-speed plunge through the densest regions. This rapid loss of gas accelerates the galaxy's transition from a star-forming spiral to an anemic, or even passive disk system. The aftermath of stripping is not just visible in the loss of gas, but in morphological changes as well. As gas is stripped away, spiral arms lose their definition. The disk becomes smoother, less chaotic. Without young stars to outline the arms and energize the interstellar medium, the structure begins to resemble that of a lenticular galaxy. This, again, reinforces the idea that anemic galaxies are not born this way. They are made through environmental processes like ram pressure stripping. Interestingly, not all galaxies are equally vulnerable. Larger galaxies with deeper gravitational wells can hold on to their gas longer. Some may resist full stripping on their first pass through the cluster, losing only their outer layers. But repeated passes, or especially deep dives into the cluster core, eventually wear them down. Smaller galaxies, particularly dwarfs, are often stripped completely in a single encounter. This differential vulnerability helps shape the population of a cluster, with small, gas-poor galaxies dominating the inner regions, and larger, still active spirals clustering along the outskirts. There's also a directional component to the stripping. Because the force acts along the line of motion, it tends to strip gas from the leading edge of the galaxy's motion and deposit it along the trailing edge. This can create asymmetries in gas distribution and star formation. One side of the galaxy appears truncated, while the other might retain patches of ongoing starbirth. Over time, even this asymmetry disappears as gas reserves are exhausted completely. From a broader perspective, ram pressure stripping plays a critical role in galaxy evolution at large. It helps explain why star-forming spirals are rare in cluster cores and why passive S0s and ellipticals dominate those environments. It contributes to the morphology-density relation, in which denser environments correlate with more evolved, passive galaxies. And it adds to our understanding of galaxy quenching, the process by which galaxies lose their ability to form stars. In many ways, ram pressure stripping is the architect of anemia. It doesn't destroy galaxies. It doesn't distort them beyond recognition. Instead, it erases their potential. It takes away the future while leaving the form. It turns dynamic, starry spirals into hushed, spinning ghosts, anemic galaxies quietly drifting through the very medium that silenced them. It's a hauntingly elegant process, an invisible wind, a silent theft, and a transformation written not in violence, but in subtraction. The galaxy continues on its course, but its voice grows quieter with every light year, until the spiral no longer sings. Beyond the searing winds of ram pressure, another force silently shapes the fate of galaxies within clusters: gravity itself. In the vast gravitational ecosystem of a galaxy cluster, no galaxy moves alone. They orbit, fall inward, and pass close to one another, and during those close encounters, they tug and twist each other's structures. These gravitational interactions, subtle yet cumulative, are known as tidal harassment, and they play a crucial role in the slow decline of spiral galaxies into their anemic forms. In a crowded cluster, galaxies are like dancers in a tightly packed ballroom, each with mass, momentum, and a gravitational field. As they move through the cluster, they experience not just the pull of the cluster's dark matter halo, but also the passing influence of their neighbors. While major mergers, where two galaxies collide and fuse, are rare in rich clusters due to the high velocities involved, high-speed flybys are common. These encounters can be fleeting, lasting only tens of millions of years, but their effects add up over time. When a galaxy passes close to another, its gravitational field can stretch and compress the stars and gas in the neighboring disk. These tidal forces can warp spiral arms, distort disks, and send ripples through the stellar populations like a stone dropped in a pond. The cumulative effect of many such interactions over billions of years can severely alter the structure of a galaxy, even if none of the encounters is strong enough on its own to cause major disruption. For spiral galaxies entering a dense cluster environment, the consequences can be devastating. As they are harassed again and again, their disks can thicken, their arms become blurred or distorted, and their cold gas, the fuel for future star formation, becomes destabilized. In some cases, gas can be funneled inward toward the galaxy's center, briefly enhancing central star formation or feeding the central black hole. But more often, the gas is heated, flung out, or slowly stripped in tandem with other environmental processes. The outer regions of the galaxy, where the gravitational hold is weakest, suffer first. Stars and gas clouds in the outskirts are most vulnerable to tidal stripping, where they can be pulled away from the galaxy and lost to the intergalactic medium, or absorbed by more massive neighbors. This not only reduces the mass of the spiral disk but also removes the parts of the galaxy most likely to host ongoing star formation. The inner disk, more tightly bound, often survives longer, but it becomes puffier, less structured, and more passive over time. Astronomers observing clusters such as Coma, Virgo, and Fornax have found numerous galaxies displaying signs of tidal distortion, warped disks, asymmetric arms, lopsided star distributions, or even faint stellar streams trailing behind. These are the fingerprints of harassment. Sometimes the changes are subtle, a faint bending of the disk or a loss of symmetry. Other times they're dramatic, a spiral arm flung out like a tendril, or a galaxy's shape stretched into a tidal bridge or tail. Harassment is not limited to flybys with other galaxies. The gravitational potential of the cluster as a whole, the combined influence of all its matter, including dark matter, also exerts a strong tidal force on any galaxy within it. This global cluster tide can shear off material from the outskirts of galaxies as they orbit the cluster center, contributing further to the stripping of mass and structure. For smaller galaxies, this can be catastrophic, leading to complete disruption. For larger spirals, it's more of a steady grind, shaving off gas and stars with each pass, reshaping the galaxy incrementally. One of the key outcomes of tidal harassment is disk heating, a process by which the orderly, rotating orbits of stars in the disk are randomized, making the disk puffier and more spheroidal. As the thin disk thickens, it begins to resemble more the structure of a lenticular or elliptical galaxy. The smooth, flat spiral becomes a rounder, redder shadow of its former self. Combine this with the loss of gas and the cessation of star formation, and the transformation into an anemic, or even passive galaxy is well underway. Interestingly, harassment doesn't always act alone. It often cooperates with other cluster processes, amplifying their effects. For instance, a galaxy already weakened by tidal encounters may become more vulnerable to ram pressure stripping. Its gas may become more diffuse or less gravitationally bound, making it easier for the cluster wind to blow it away. Similarly, a galaxy that's been partially stripped of gas may experience further destabilization from gravitational interactions, hastening its decline. This makes tidal harassment not just a standalone mechanism, but a co-conspirator in the slow silencing of galaxies. It doesn't need to be violent to be effective. It chips away at a galaxy's order and structure, pushing it down the evolutionary path. In many ways, it's like the weathering of a mountain, gradual, persistent, and inevitable over time. Simulations of cluster environments have confirmed this process in exquisite detail. High-resolution models show that even without direct collisions, galaxies and clusters experience significant morphological and dynamical changes simply through repeated gravitational nudges. These changes match the properties we observe in anemic galaxies today: smoother disks, reduced star formation, faded arms, and disrupted symmetry. In the simulations, we watch spiral galaxies transform over billions of years, not in explosions, but in a slow unraveling caused by their crowded, dynamic surroundings. This leads to a compelling insight. Anemic galaxies are not relics of a unique formation path, but natural waypoints in a broader evolutionary journey. They are the battered survivors of gravitational harassment, shaped by the cluster's collective pull and the jostling of countless neighbors. They remind us that galaxy evolution is not always explosive or cataclysmic. Sometimes, it's a whisper of gravity, repeated over and over, until the spiral fades. In a way, the beauty of tidal harassment lies in its subtlety. It's a sculptor working not with chisel and hammer, but with invisible hands, reshaping galaxies across cosmic time, quietly nudging them towards stillness. And in anemic galaxies, we see the result: once bright spirals, worn smooth by the tides of the cluster, spinning gently in the long twilight of galactic life. To truly understand the evolution of anemic galaxies, astronomers often look to a particular region of the sky, not far in cosmological terms, but rich in complexity and clues. This region is the Virgo cluster, our nearest major galaxy cluster, and it serves as a kind of cosmic laboratory for studying how galaxies change, fade, and transform under environmental pressure. It was here, among the thousands of galaxies packed into Virgo's gravitational grip, that astronomers first identified large numbers of anemic spirals. And it's here that the fingerprints of galactic fading are clearest, cleaving open the mystery of how spiral galaxies lose their brilliance and become quiet, passive husks of their former selves. Located roughly 55 million light-years away in the constellation Virgo, the Virgo cluster is the heart of the Virgo supercluster, the larger structure that includes our own local group. The cluster contains more than 1,300 confirmed galaxies, with estimates rising to over 2,000 when accounting for faint and dwarf members. Its proximity makes it an ideal target for detailed observation across the electromagnetic spectrum, optical, radio, infrared, and ultraviolet alike. Unlike more distant clusters that appear as dense, compressed smears of light, the Virgo cluster offers individual, resolvable galaxies, each one a separate case study in cosmic evolution. Within this enormous celestial community, astronomers began noticing something strange in the 1970s and 1980s. Many galaxies that still look like spirals, with disks, bulges, and even traces of arms, were missing something essential. They were unusually red, deficient in gas, and lacking active star-forming regions, especially in their outer disks. Their spiral arms were faint, ghostly, or sometimes barely visible. It was in Virgo that Alan Sandage and others first applied the term, anemic galaxy, to describe this phenomenon, galaxies that seemed structurally spiral but were fading fast in terms of stellar activity. Why is Virgo such a hotspot for these galaxies? The answer lies in the cluster's environment. Virgo is not a static or relaxed cluster. It's dynamically young, with substructures, infalling galaxy groups, and a complex web of gas and dark matter. The intracluster medium, a hot, X-ray emitting plasma, weaves throughout, creating the conditions necessary for ram pressure stripping, as galaxies fall into the cluster and plow through the medium. This environment makes Virgo an active site of galaxy transformation, where galaxies are in the very act of being quenched. Many galaxies in Virgo are spirals in distress. Observations from radio telescopes show that their neutral hydrogen is asymmetrical, truncated, or entirely missing, signs of ongoing or recent gas stripping. Some, like NGC 4569 M90, retain a central region of star formation but have lost most of their outer gas. Others, like NGC 4522, are clearly undergoing ram pressure stripping right now, with HI tails trailing behind them as they move through the cluster's plasma. These are not random anomalies. They are part of a pattern seen over and over again in Virgo. Moreover, surveys like the VLA imaging of Virgo in atomic gas (VIVA) project have cataloged and mapped the HI content of dozens of Virgo spirals, confirming that HI deficiency correlates strongly with cluster location. Galaxies near the core, especially those moving at high velocities relative to the cluster center, are more likely to be stripped of gas and show signs of anemia. Those on the outskirts tend to retain their gas and continue forming stars, although even they may eventually fall inward and face the same fate. Virgo's diverse population of galaxies also allows astronomers to see multiple stages of transformation. Some galaxies are just beginning their journey into quenching. Their star formation has declined, but spiral arms and gas reservoirs remain. Others are more advanced. Their disks are smooth, their gas is gone, and their colors have shifted entirely to red. Still others have fully transitioned into lenticulars, smooth disk galaxies with no visible spiral structure at all. This evolutionary continuum is visible within a single cluster, a time-lapse of galactic aging spread across space instead of time. The Virgo cluster also offers insight into the role of harassment, the gravitational interactions between galaxies that contribute to their structural decline. The cluster's crowded environment leads to frequent close passes between galaxies, and while these don't always result in mergers, they can warp, heat, and disturb spiral disks. Combined with gas stripping, these encounters accelerate the fading process, nudging galaxies further into anemic states or even transforming them completely. In essence, Virgo serves as a snapshot of transition. It captures galaxies that were likely once vibrant field spirals, now being subjected to the cluster's hostile weather. It lets astronomers study how star formation fades, how spiral arms erode, and how gas reservoirs vanish, not in isolation, but as part of a broader ecological shift. Anemic galaxies in Virgo are not curiosities. They are common, predictable, and revealing. They tell the story of transformation not just through their own properties, but through their distribution, orientation, and motion within the cluster. This is why Virgo continues to be studied in such depth, by professional astronomers with powerful instruments, and by amateur observers with backyard telescopes alike. It's nearby, complex, and in flux. And it holds the keys to one of the great mysteries of galaxy evolution, how a universe once filled with youthful, star-forming spirals has gradually grown older, quieter, and redder. In Virgo's core, we see the gentle hush falling over spiral galaxies. Not a sudden extinction, but a slow dimming, a cosmic twilight driven by the heat, gravity, and motion of their surroundings. And in that hush, we find the clearest clues to the origin and fate of anemic galaxies. One of the most profound discoveries in extragalactic astronomy is that galaxies do not evolve in isolation. Their fate, shape, and activity are influenced not only by their internal structure or mass but by where they live in the cosmos. This idea, that a galaxy's environment plays a significant role in shaping its morphology, is encapsulated in what's known as the morphology-density relation. And few types of galaxies illustrate this concept more vividly than the anemic spirals quietly fading in the dense hearts of clusters. The morphology-density relation was first quantified in the 1980s by astronomers such as Alan Dressler, who surveyed thousands of galaxies and found a clear pattern. Spiral galaxies are more common in low-density environments, like the outskirts of clusters or in the field, while elliptical and lenticular galaxies dominate in high-density environments, such as the cores of rich clusters. This correlation implies that a galaxy's structure is not purely determined by how it formed, it is also shaped by the company it keeps. In other words, galaxies that live in isolation tend to retain their disks, spiral arms, and star-forming vitality. But galaxies that move into crowded, gravitationally complex environments, like those found in clusters, are more likely to lose their gas, shut down star formation, and become smooth, red systems with little internal structure. The deeper a galaxy moves into a cluster, the more likely it is to undergo this kind of morphological transformation. Anemic galaxies sit at a key inflection point in this relation. They are spirals by classification but not by behavior. They inhabit regions where spiral galaxies are increasingly rare, the intermediate density zones between the cluster core and its outskirts. In these regions, environmental effects are strong enough to begin transforming spirals but not yet complete enough to erase their structure entirely. This is why anemics are often found. They are spirals in transition, already redder and more passive than their field counterparts but not yet fully quenched. Studies of galaxy clusters such as Virgo, Coma, and Fornax consistently show this trend. As you move from the periphery of the cluster toward the dense core, spiral galaxies become fewer, and those that remain show signs of distress, truncated star-forming disks, reduced gas content, and fading spiral arms. These are the anemics, the morphological middle ground between healthy, gas-rich spirals and gas-poor, structureless S0s or ellipticals. Their presence reinforces the idea that morphological change is not binary, it's a spectrum, with galaxies evolving in stages based on their position in the density gradient. And this relationship holds not just in the local universe, but also at higher redshifts, when galaxy clusters were still forming and denser environments were more dynamic. Observations of distant clusters show similar transitions, suggesting that the morphology-density relation has been in place for billions of years. This means that anemic galaxies are not just a local curiosity, they are part of a universal process that has shaped galaxies across cosmic time. Interestingly, simulations of galaxy formation and evolution also reproduce this trend. Large-scale cosmological simulations like Illustris and Eagle show that galaxies falling into dense environments often experience a decline in star formation, driven by processes like ram pressure stripping, tidal interactions, and gas starvation. The morphological changes that follow, disk fading, spiral disruption, color evolution, all proceed in ways that mimic the real galaxies observed in clusters today. In these virtual universes, anemic galaxies arise naturally as part of the ecological adaptation of galaxies to their environments. The morphology-density relation also challenges our understanding of galaxy classification. Traditional systems, like Hubble's tuning fork diagram, assign galaxies to rigid categories, spiral, elliptical, lenticular, as though these were permanent states. But the reality revealed by the morphology-density connection is more fluid. Galaxies move through different environments, and those environments shape them in ways that may nudge them from one classification to another. A spiral galaxy today may be a lenticular tomorrow, not through some catastrophic change, but through the slow grind of environmental influence. Anemic galaxies, therefore, are not outliers or exceptions. They are a natural consequence of this relation, galaxies that are exactly where we expect them to be, undergoing the kinds of changes predicted by the density of their surroundings. They are the evolutionary proof that the universe is not a passive backdrop but an active agent in shaping its inhabitants. And this insight ripples outward. It means that to understand a galaxy fully, we cannot just look at its shape, color, or spectrum. We must also ask, where is it? What's around it? How dense is its neighborhood? A galaxy's morphology is as much a record of its environment as it is of its birth. In the quiet spiral arms of an anemic galaxy, we read the story of place, a story not of what the galaxy is, but of what it's becoming, and why. The anemic galaxy is not a strange exception or a failed spiral. It may very well be the natural destiny of many once vibrant galaxies that have begun the long descent into cosmic quietude. For decades, astronomers puzzled over the sharp contrast between the abundance of blue, star-forming spiral galaxies in the field and the dominance of red, smooth systems in clusters. What bridges that gap? Increasingly, evidence suggests that many spiral galaxies are not destroyed but gradually dimmed, fading into the anemic class before transforming further into lenticulars, or even ellipticals. These fading giants are not dying suddenly. They are cooling down, slowing down, and quietly aging, one lost gas cloud at a time. Spiral galaxies are typically associated with youth. Their open, sweeping arms trace the orbits of hot, young blue stars, the short-lived beacons of active star formation. Their disks are rich in cold hydrogen gas, the raw material from which new stars are born. Their structures are often asymmetric, irregular, and dynamic, evidence of an ongoing internal and external conversation with their environments. But all of this activity is contingent on one thing: fuel. The moment the supply of gas is cut off or depleted, the star factories slow down. The arms begin to fade. The color shifts. And the once lively spiral takes on the first symptoms of anemia. The process is so gradual that we rarely catch it in real time, but in the statistical data, in galaxy surveys across multiple environments and redshifts, the pattern becomes clear. Star formation doesn't halt overnight. It declines. The inner disk may continue forming stars for a while, even as the outer regions shut down. But without replenishment, the galaxy slowly transitions into a state of quiescence, maintaining its structure but losing its brightness, both literally and metaphorically. One might wonder, how does a galaxy lose its fuel in the first place? The answer isn't always dramatic. Some galaxies are stripped of gas by environmental forces like ram pressure or tidal harassment, especially in clusters. But even in isolation, galaxies can fade. If a galaxy consumes its gas faster than it can acquire more, it will naturally shift toward a quieter phase. This is known as gas starvation, or strangulation, and it's surprisingly common. The inflow of fresh gas from the cosmic web slows down, or is cut off entirely by processes in the galaxy's own halo or feedback from a central black hole. Star formation then declines, not because of a violent event, but due to a slow suffocation. This process results in what we might call galactic middle age. The galaxy still retains its spiral disk, its bulge, even its rotation, but it's no longer birthing stars at a significant rate. The once bright arms, no longer replenished by hot, young stars, grow fainter. The light from older, redder stars begins to dominate. The galaxy becomes what Alan Sandage first called anemic, structurally spiral, but dimmed in activity. And this is not hypothetical. We see it across clusters like Virgo, where numerous spirals are still intact but redder and smoother than expected. They're not yet lenticulars, but they're clearly in the process of transformation. They rotate like spirals but glow like ellipticals. They are caught in the act of fading. Some still contain remnants of gas and occasional patches of star formation, like embers left in a cooling fire. But overall, the light is dimming, the structure softening, the pace slowing. What's fascinating is that these fading giants might once have looked like the Milky Way. Our own galaxy, currently rich in star formation and complex spiral structure, may one day fall into a more crowded environment, a cluster, perhaps, and begin the same descent. Or it may simply use up its gas over billions of years. In either case, its future might resemble the anemic galaxies we now study. The image is sobering, not an explosion, not a collapse, just a slow dimming of cosmic vitality, a twilight that spreads across the spiral arms. Simulations support this gradual fading model. They show that galaxies don't need to merge or be disrupted to transform. A gentle change in environment, a drop in inflow, a period of low interaction, that's all it takes. Over gigayears, the galaxy's gas content dwindles, the balance of stellar populations shifts, and the outward appearance changes from blue to red, from complex to smooth. And somewhere along that continuum lies the anemic galaxy, a galaxy in the middle of saying goodbye. These fading giants are a crucial piece of the cosmic puzzle. They help us understand how the universe shifted from its youth, dominated by active, blue galaxies, to its current maturity, where red and dead systems are common. They remind us that transformation doesn't always come with fireworks. Sometimes it comes in silence. The last stars form. The arms grow still. The spiral continues spinning, but no longer sings. As galaxies age and evolve, their colors change, not just aesthetically, but fundamentally, in a way that reflects the life cycle of the stars within them. Anemic galaxies, in particular, exhibit a telling shift in hue. They tend to glow with a soft red or yellowish light, much different from the brilliant blues often associated with youthful spiral galaxies. This reddening is not superficial, it's a cosmic diagnosis. It reveals a slowdown in stellar birth, a population aging in place, and the gradual fading of galactic vibrancy. In the story of the cosmos, color is not just decoration, it's a language, and in anemic galaxies, that language speaks of stars that are growing old with little to replace them. The color of a galaxy is essentially the sum of the light from all its stars. And stars come in a wide range of colors depending on their temperature, size, and age. Young, massive stars burn hot and fast, emitting intense ultraviolet and blue light. They live short, dramatic lives, often ending in supernova explosions within a few million years. Their presence gives star-forming galaxies, particularly spiral arms, a bright blue glow. These hot stars act as beacons of youth, making it easy for astronomers to spot galaxies teeming with stellar nurseries. On the other end of the spectrum, older stars, typically lower in mass, burn cooler and longer. These are red or yellow stars, like our Sun or the even cooler red dwarfs. As a galaxy stops forming new stars, its hot, young population gradually fades out, leaving behind the longer-lived redder stars to dominate the light. Over hundreds of millions of years, this slow demographic shift causes the galaxy to redden overall. The transformation from blue to red is not a matter of paint drying, it's a record of stellar generation loss. In anemic galaxies, this shift is clearly underway. While their overall structure might still resemble a spiral, with disks, arms, and bulges, the light they emit tells a different story. Their integrated color spectrum shows a higher proportion of red and yellow light, and less from the ultraviolet and blue end. This is a direct result of diminished star formation. Without a steady influx of hot, young stars to replenish the galaxy's energy budget, the older, cooler population becomes the dominant voice. This reddening has been carefully catalogued by astronomers using both ground-based observatories and space telescopes like Hubble, Galax, and Spitzer. Broad color indices, such as B-V and U-B magnitudes, are used to quantify the overall color of a galaxy. In active spirals, these values are relatively low, indicating strong blue and ultraviolet light. In anemic galaxies, the indices shift toward the red, placing them in an intermediate color zone, not as red as ellipticals, but clearly departing from the blue end of the spectrum. These colors also map directly onto stellar population models, which allow astronomers to estimate the ages of stars within galaxies based on their light. An anemic galaxy often has a stellar population with a mean age of several billion years, with very few stars younger than a few 100 million. The bright blue stars are gone, their supernovae echoes long past. What remains is the glow of a mature stellar society, long-lived, steady, and slowly cooling in the absence of renewal. But color is not just about age, it also speaks to metallicity and dust content, two additional factors that shape a galaxy's appearance. In anemic galaxies, the dust content tends to be lower, since dust is often tied to active star-forming regions. Less dust means less light scattering and absorption, allowing the intrinsic color of the older stars to shine through more clearly. And with star formation dwindling, so too is the enrichment of metals, since massive stars are the primary forges of heavier elements. The result is often a chemically modest galaxy, with subtle gradients in color that mirror its quiet internal chemistry. These color changes are not merely cosmetic, they're diagnostic tools in the study of galaxy evolution. They allow astronomers to place galaxies on the so-called color magnitude diagram, a galactic version of the Hertzsprung-Russell diagram used for stars. On this graph, galaxies cluster into two main groups, the blue cloud, where star formation is active and galaxies are bright in ultraviolet and blue light, and the red sequence, where galaxies are old, passive, and dominated by ancient stars. Anemic galaxies sit in the in-between zone known as the Green Valley, a transitional space that hints at their evolutionary trajectory. They are fading out of the blue cloud but not yet fully settled into the red sequence, evidence that we are witnessing them in motion, not just in space, but in time. This cosmic color coding is critical for understanding not just the galaxies themselves, but the larger story of the universe. As the cosmos ages, the overall population of galaxies has shifted from blue to red. Billions of years ago, most galaxies were active, messy, and bright with new stars. Today, the universe is calmer, and red, passive galaxies dominate the census. Anemic galaxies, with their still spiral structure and faded light, serve as the missing link in that transformation, living proof of the slow but inevitable march from fire to ash. And yet, the reddening of an anemic galaxy is not always final. Some still harbor pockets of cool gas and residual star formation. In ultraviolet surveys, faint traces of youth can sometimes be detected, lurking in the shadows of the old. A spiral arm might glow faintly. A central region may still flicker with new birth. These fragments hint at the possibility of revival, of a temporary pause rather than a permanent silence. But for many, the journey is one of quiet decline. The blue lights fade, the arms soften, and the galaxy turns inward, bathed in the steady glow of its ancient stars. The red light of an anemic galaxy is not fiery like a sunset, it's more like embers still warm, but cooling with every passing million years. It's the color of a galaxy that remembers being young, now content to drift in a slower rhythm, a visual elegy painted in fading light. While light and color reveal the age and activity level of a galaxy's stars, another critical ingredient often shapes what we see, or don't see, when we look at a galaxy: dust. In active, star-forming galaxies, dust is everywhere. It absorbs and scatters starlight, cloaks bright regions in shadowy veils, and glows in infrared when warmed by nearby stars. Dust is both a product and a partner in stellar birth, helping cool gas clouds so they can collapse into stars, and tracing the chaotic currents of a bustling galactic disk. But in anemic galaxies, that chaos fades. Their appearance becomes smooth, undisturbed, and cleaner, not because of clarity, but because the dust itself is missing or severely depleted. And this absence is no small detail. It's a key signal that the galaxy is quiet, calm, and winding down. In galaxies like our Milky Way, dust is created primarily in the late stages of stellar evolution. Aging stars, particularly red giants, shed their outer layers into the interstellar medium. Supernova explosions also contribute dust, enriching the surrounding gas with heavy elements like carbon, silicon, and iron. Over time, this material coalesces into microscopic grains that drift through the galaxy, forming dusty lanes, veils, and clouds. These dusty regions are not just decorative, they are often the birthplaces of stars, marking areas dense with gas and shielded from external radiation. But dust doesn't last forever. It can be destroyed by intense radiation, shocks, or collisions. More importantly, if the supply of new dust isn't maintained, through ongoing stellar death or robust star formation, a galaxy's dust content will gradually decline. And that's exactly what we see in anemic galaxies. Anemic spirals often exhibit remarkably smooth, dust-free disks. Their images, taken in visible light, show little of the mottled texture and dark patches that characterize active spirals. Instead, their surfaces appear evenly illuminated, lacking the telltale dark lanes of interstellar dust. This doesn't mean they never had dust, quite the opposite. It means the engines that produce and maintain dust have slowed or stopped, along with star formation. Without young stars lighting up dusty regions, and without massive stars exploding into dust-creating remnants, the dusty tapestry of the interstellar medium begins to fade away. The reduction in dust contributes directly to the clean, undisturbed look of these galaxies. In some ways, it's deceptive. They still rotate, they still contain billions of stars, and they may even retain some residual gas. But the absence of dust lends them a passive aesthetic, a sense of cosmic tranquility. The galaxy looks like it has settled into a final form, no longer reshaped by the turbulence of stellar birth or supernova feedback. Observations in infrared and submillimeter wavelengths, where dust glows most brightly, confirm this stark difference. Instruments like Spitzer, Herschel, and ALMA have measured much lower dust emission in anemic galaxies compared to their active spiral counterparts. This isn't just a function of fewer young stars, it's a literal reduction in dust mass. And since dust is often tied to the presence of cold molecular gas, the fuel for star formation, this lack further reinforces the idea that these galaxies are out of gas, literally and figuratively. Interestingly, the absence of dust also has an observational benefit. It gives astronomers a clearer view of the stellar populations and internal structures within these galaxies. Without dust lanes obscuring light, the true shapes of the bulge and disk stand out more distinctly. This has allowed for more accurate measurements of their stellar kinematics, surface brightness profiles, and age distributions, data that further confirm their faded, aging nature. The smoother light profile is also tied to their calmer dynamics. In a star-forming galaxy, dust often traces turbulent flows, driven by the gravitational collapse of gas clouds and the feedback from young stars. These processes stir the interstellar medium, creating ripples and bursts of structure in both light and matter. Anemic galaxies, by contrast, have settled. With little dust to trace motion, and little gas to disturb the stellar disk, their appearances take on a stillness that reflects their internal calm. It's as if the galaxy has taken a deep breath and stopped inhaling. Moreover, this low-dust state has consequences for the cooling of remaining gas. Dust grains play a critical role in helping gas clouds radiate away energy, a necessary step in the formation of stars. Without enough dust, even if some cold gas lingers in the galaxy's disk, it may be unable to cool efficiently enough to collapse and spark new stars. Thus, the loss of dust doesn't just reflect the end of star formation, it can perpetuate it, preventing any potential rebound into activity. In this way, dust, or its absence, acts like a thermostat and a symptom rolled into one. It tells us what the galaxy has been doing recently, and it also influences what the galaxy is able to do in the future. And in anemic galaxies, the message is clear: the cycle has slowed. The dust clouds have dispersed or been destroyed. The raw materials for birth have been used up or carried away. And the galaxy, while still holding its shape, has entered a quieter, more reflective phase of existence. When we look at these dust-free disks, we're not seeing emptiness, we're seeing the echo of activity past. It's a visual signature of peace, not because the galaxy is healthy, but because it's no longer restless. The dust has settled. The chaos has subsided. And what's left is the elegant, uninterrupted glow of starlight, unfiltered, unshadowed, unrenewed. Peering into an anemic galaxy is like examining the faded pages of a well-worn history book, quiet on the surface, yet layered with stories of what once was. When astronomers look beyond the dimmed arms and the reddened light, they find the galaxy's deeper truths embedded in its stellar populations. These are the stars that remain after the cessation of active birth, the survivors of a long and slowly cooling cosmic fire. Understanding what kinds of stars dominate anemic galaxies, and what those stars are made of, reveals the intricate inner structure of these fading systems and the chemical trail of their former lives. At a glance, the majority of stars in an anemic galaxy are older and lower mass than those found in vibrant spiral galaxies. This isn't surprising. Without new stars being formed, the population ages. The most massive stars, those that live fast and die young, vanish quickly, often within a few million years. What remains are the red giants, subgiants, and long-lived main sequence stars that glow steadily for billions of years. These stars, cooler and redder, dominate the galaxy's light, especially in the absence of young, blue O and B-type stars. This aged stellar population isn't just uniform in color, it tells a story of star formation history. Through techniques like spectral synthesis modeling, astronomers can reconstruct how the galaxy formed stars over time by analyzing its light. Each type of star contributes a unique spectral fingerprint, absorption lines corresponding to elements like hydrogen, calcium, iron, magnesium, and more. By studying the strengths and shapes of these lines, scientists can estimate not just the ages of the stellar populations, but their metallicity, a measure of how enriched the stars are in elements heavier than helium. In anemic galaxies, the average metallicity tends to be moderately high, especially in the inner regions. This suggests that these galaxies had prolonged periods of star formation in the past, during which successive generations of stars enriched the interstellar medium with heavier elements. Over time, each wave of star formation added more metals to the gas, resulting in younger stars, now aging, that were born from more chemically enriched material. This metallic signature is typical of galaxies that have lived long and rich star-forming lives, now winding down. Interestingly, metallicity is not uniform across anemic galaxies. In many cases, there exists a radial gradient, with the central bulge containing older, more metal-rich stars, and the outer disk, where star formation has been shut down for longer, housing relatively younger, but still aging, populations with slightly lower metal content. This gradient offers insight into how the galaxy evolved from the inside out, perhaps retaining gas in the center longer than in the outer disk, allowing central star formation to persist, while the outskirts grew quiet. One of the most fascinating aspects of studying these stars is identifying the chemical fingerprints of different stellar populations. For instance, the ratio of alpha elements, like magnesium, oxygen, and silicon, to iron can tell astronomers about the timescales of star formation. Alpha elements are produced in core collapse supernovae from massive stars, which occur quickly after star formation begins. Iron, on the other hand, is significantly produced in type I supernovae, which take longer, often over 1 billion years, to explode. A high alpha to iron ratio suggests rapid, intense star formation that was cut off before many type I supernovae could contribute iron. A lower ratio implies slower, extended star formation, giving time for iron to accumulate. In anemic galaxies, the alpha to iron ratios tend to indicate a more prolonged star formation history than in elliptical galaxies, but not as extended as in healthy spirals. They sit in the middle ground, consistent with a galaxy that was once active for a long time but then experienced a gradual cessation of star birth. These chemical traces are like cosmic archaeology, helping reconstruct a timeline of events from long-extinct stellar generations. Furthermore, the kinematics of these stars, their motions through the galaxy, also reveal key distinctions. In many anemic galaxies, the disk stars continue to exhibit rotational motion, though sometimes slower and more dispersed than in fully active spirals. This suggests that the structural identity of the spiral disk remains intact, even as its population has aged. The stars have not collapsed into a spheroid or been randomized as they might in a merger. Rather, they've aged in place, continuing their quiet orbital dance around the galactic center. In some cases, the presence of blue horizontal branch stars or UV-bright low-mass stars in older populations may provide limited ultraviolet light, detectable in sensitive observations. These stars are not newly born but are rather old stars in exotic evolutionary phases. Their presence adds subtle complexity to the otherwise red-hued appearance of the galaxy, offering hints that even in aged populations, not all activity has ceased. Ultimately, the stars within an anemic galaxy paint a picture of longevity and loss. They are the fossilized echoes of epochs of star formation, billions of years where the galaxy lived as a vibrant spiral, building layers of stellar generations and enriching its own composition. Now, in the absence of gas and dust, these stars remain, a population of retirees, so to speak, glowing faintly as the galaxy coasts into its later years. Their light, though faded, is far from meaningless. It holds the keys to understanding not just the history of an individual galaxy, but the grand evolutionary trajectory of galaxies across the universe. By decoding their chemical fingerprints, astronomers glimpse the birthplaces of the elements, the rhythm of ancient starbursts, and the turning of the cosmic clock, all preserved in the hushed glow of stellar memory. In the great machinery of the cosmos, galaxies are the engines of creation, and like any engine, they need fuel to run. In this case, the fuel isn't oil or electricity, but cold gas, particularly neutral hydrogen, Hi, and molecular hydrogen, H2. This gas condenses into dense clouds, collapses under gravity, and ignites the fusion furnaces we call stars. But in anemic galaxies, this fuel is scarce or altogether absent. The tanks are running dry. And without that essential ingredient, the star-making machinery stalls. This is the quiet truth at the heart of these fated spirals: no gas, no party. The connection between gas and star formation is one of the most fundamental relationships in astrophysics. Observations of thousands of galaxies across all types and environments have revealed a clear trend. Where gas is abundant, star formation is active. Where gas is depleted, the birth of new stars dwindles or ceases entirely. This relationship is not just observational, it's causal. Stars form from gas. Without gas, star formation is simply impossible. In healthy spiral galaxies, cold atomic hydrogen exists in large reservoirs, typically traced using the 21 centimeter line in radio observations. This HI gas resides mostly in the outer disk and acts as a vast reserve. Through various processes, gravitational instability, interactions, or spiral density waves, this atomic gas collapses into molecular clouds, which are colder, denser, and ready for star formation. The molecular hydrogen, often traced via carbon monoxide (CO) emissions, marks the actual sites where stars are born. But in anemic galaxies, this whole sequence is disrupted. Surveys have shown that they are severely deficient in both HI and H2. Radio observations reveal truncated HI disks or complete HI depletion, especially in cluster environments like Virgo. In many cases, the atomic hydrogen that remains is restricted to the inner regions, while the outer disk, typically the most fertile area for star formation, has been stripped clean. And if the atomic gas is gone, molecular gas production also suffers, cutting off the very source of stellar birth. This gas loss is not always the result of internal processes. In clusters, external mechanisms like ram pressure stripping can forcibly remove gas from the galaxy as it plunges through the hot intracluster medium. Imagine a galaxy flying through a wind of superheated plasma. The pressure pushes against the galaxy's gas, stripping it away from the disk, especially in the less gravitationally bound outer regions. This is one of the most efficient ways to shut down star formation. It doesn't just pause the cycle, it removes the fuel altogether. Other galaxies may experience gas starvation, also known as strangulation. In this scenario, a galaxy's supply of fresh gas from the cosmic web is cut off, either because it enters a dense halo environment where infalling gas is heated and prevented from cooling, or due to feedback mechanisms like AGN activity that expel or heat the gas. Without fresh inflow, the galaxy must rely solely on its existing reserves. Over time, those reserves are consumed by ongoing star formation, and the galaxy slowly fades into quiescence. In either case, stripping or starvation, the result is the same. With gas gone or inaccessible, star formation plummets. In anemic galaxies, this is seen most clearly in the suppression of HI regions, the glowing clouds of ionized hydrogen that mark sites of active star birth. In normal spirals, these regions are scattered throughout the disk, especially along spiral arms. In anemics, they are rare or entirely missing, a ghostly silence replacing what was once a riot of stellar formation. The few HI regions that do remain are typically weak and confined to the inner disk or bulge, where gas may linger longer due to deeper gravitational wells. But even these oases are temporary. Without resupply, even the central star formation will fade, and the galaxy will transition further toward full quiescence, possibly becoming a lenticular, S0, galaxy, still disk-like, but fully passive. It's worth noting that the relationship between gas and star formation is not just binary. It follows a well-known scaling law, the Kennicutt-Schmidt relation, which links the surface density of gas to the surface density of star formation. In anemic galaxies, this relation still holds, but the gas density is so low that the corresponding star formation is negligible. The law isn't broken, it's obeyed all too faithfully. The galaxy simply operates at the lower extreme of the scale, where the transformation of gas into stars becomes inefficient or impossible. Interestingly, some anemic galaxies may retain small amounts of molecular gas, but still fail to form stars efficiently. This could be due to high turbulence, stabilizing rotational forces, or low cloud density, all of which can prevent molecular clouds from collapsing. In these cases, the galaxy has fuel, but no ignition. The molecular gas remains inert, a latent reservoir unable to spark new life. The consequences of gas depletion ripple through every aspect of a galaxy's evolution. Without new stars, there are no supernovae to enrich the interstellar medium with metals. No young stars to stir up turbulence or feedback. No ultraviolet light to ionize nearby gas. The entire galactic ecosystem slows down. The stellar population ages. The light reddens. The dust dissipates. The galaxy becomes not just quieter, but chemically and structurally frozen, a system that is no longer evolving in the traditional sense. In many ways, the loss of gas marks the moment a galaxy transitions from growth to memory. It no longer builds. It only endures. The absence of star formation becomes not just a state, but a story, one of exhaustion, depletion, and environmental pressure. And in the case of anemic galaxies, that story is written in every quiet corner of their faded disks, every missing HI region, and every spectral signature of stellar stillness. The party is over, not because the lights went out, but because the bar ran dry. The galaxy continues to spin, but the fuel is gone, and in the vast darkness of space, no gas means no new light. The story of anemic galaxies is more than an isolated curiosity. It's a quiet, crucial chapter in the grand saga of galaxy quenching. In cosmology, quenching refers to the process by which galaxies shut down or severely reduce their star formation, transforming from active, blue, gas-rich systems into passive, red, gas-poor ones. It's the difference between a galaxy that's building its future and one that's living in its past. And while this transformation can occur through many mechanisms and on different timescales, anemic galaxies offer a snapshot mid-transition, a living demonstration of how the light slowly fades, not with a bang, but with a long, cosmic exhale. To understand where anemic galaxies fit into this narrative, we have to first grasp the two main modes of galaxy quenching: mass quenching and environmental quenching. Mass quenching refers to internal processes that shut down star formation, often tied to the galaxy's own size or activity. Large galaxies, especially those with massive central black holes, can experience AGN feedback, where energy from the active nucleus heats or expels gas, preventing it from cooling and forming stars. Alternatively, the galaxy's dark matter halo may grow so massive that infalling gas gets shock-heated, forming a hot corona that's unable to cool efficiently. In both cases, the galaxy starves itself. It chokes on its own energy. These are dramatic, often violent forms of quenching, and they are typically associated with massive ellipticals or compact quiescent galaxies. Environmental quenching, by contrast, occurs when external forces, such as interactions with other galaxies or the intergalactic medium, remove or suppress the gas supply. This is the domain of ram pressure stripping, tidal harassment, gas starvation, and strangulation. These mechanisms don't necessarily disrupt the structure of the galaxy. Instead, they gradually remove its fuel or prevent new fuel from arriving. Over time, the galaxy's star formation declines and eventually halts. This is where anemic galaxies shine, not literally, but conceptually. They are the visible evidence of this slow external quenching in action. In many cases, anemic galaxies are found in dense environments like galaxy clusters, where these environmental effects are most potent. Their faded spiral arms, low gas content, and reduced star formation are telltale signs of a system that is no longer self-sustaining, but also not yet dead. They are in transition, and that transitional state is exactly what makes them so valuable. They are not fully quenched like S0 or elliptical galaxies, but they are no longer fully active either. They occupy the gray zone, the fading bridge between the blue cloud and the red sequence. In the broader landscape of galaxy evolution, this transition is vital. The universe didn't always look like it does now. Billions of years ago, the majority of galaxies were active, forming stars at high rates, glowing with ultraviolet and blue light, interacting, merging, building structure. But over cosmic time, the number of passive galaxies has grown. The universe is aging, and with age comes quiescence. Quenching is how the universe transforms its population, not by destroying galaxies, but by quieting them. And anemic galaxies help us understand how that transformation occurs, gradually, subtly, and often invisibly to the naked eye. They show us that quenching isn't always fast. There's no universal, off, switch for star formation. Sometimes the gas is stripped away in an instant, and sometimes it takes a few billion years for a galaxy to exhaust its fuel or drift into a denser region where inflow is suppressed. The presence of anemic galaxies in intermediate density environments, not quite the outskirts, but not the cluster cores either, highlights the slow, environmental edge of the quenching spectrum. There's also a temporal dimension to this. Galaxies that are now passive must have gone through a stage of decline. And yet, such transitional objects are rare, which means the phase is either rapid and hard to catch, or subtle and easy to overlook. Anemic galaxies suggest the latter. Because their structure remains spiral, we might mistake them for healthy disks. But their gas and star formation profiles tell another story. They're quieting galaxies disguised in familiar clothes. And that makes them one of our best tools for mapping the timing and mechanics of quenching in the nearby universe. Additionally, in cosmological simulations, like those from Illustris, Eagle, or TNG, quenching emerges as a key process in shaping the galaxy population we see today. The models predict that many galaxies, especially in clusters, experience extended periods of low-level star formation before becoming truly passive. The simulated versions of these galaxies match the observed properties of anemic galaxies quite well: spiral morphology, reduced but non-zero star formation, and declining gas content. The match is so close that anemic galaxies are sometimes referred to in simulation literature as green valley disks, the visible stepping stones from activity to stillness. Even in terms of demographics, anemic galaxies provide valuable statistics. By counting how many of them exist in a cluster, and comparing that number to fully active and fully passive galaxies, astronomers can estimate quenching timescales, how long it takes a galaxy to go from blue to red, from full throttle to coasting. Estimates range from a few 100 million to several billion years, depending on the galaxy's mass and location. Without anemic galaxies to anchor those estimates, the transition would remain mostly theoretical. Finally, there's the emotional undertone to quenching, a realization that galaxies, like stars and planets and perhaps civilizations, have life cycles. They are born in clouds of gas, they flourish in vibrant star-forming youth, and they age. Anemic galaxies capture that aging process in its middle act. They are not dead. They are graying. And that grayness, both literal in their light and metaphorical in their place between extremes, offers a deeply human connection to cosmic evolution. They are reminders that change isn't always dramatic, that decline can be graceful, and that silence follows song, not as failure, but as an inevitability. In the big picture, quenching is what shapes the modern universe. Anemic galaxies are not just part of that story, they are the quiet evidence of its progression. The image of anemic galaxies as fading giants drifting into oblivion is compelling, but is it the full story? While much of the evidence points to these galaxies being in decline, another possibility lingers at the edge of our understanding. What if they're not dying, but sleeping? Could anemic galaxies, seemingly stripped of their vitality, actually be in a dormant phase, waiting for a spark, a change in environment, a fresh influx of gas, to reignite their star-making engines? To explore this idea, we must first consider the reversibility of galaxy evolution. In many astrophysical processes, time is a one-way street. Stars age and die, entropy increases, and gravitational collapse is nearly impossible to undo. But galaxies, especially disk galaxies like spirals and their anemic cousins, exist on longer and more flexible timescales. The internal processes that define their state, gas cooling, star formation, feedback, accretion, can ebb and flow with external influence. So while quenching is often viewed as a terminal phase, temporary dormancy is a viable, even observed, possibility in some cases. Anemic galaxies, with their intact spiral structure and residual rotation, haven't yet collapsed into the spheroidal shapes of fully passive systems. That structural integrity matters. It means the framework for star formation still exists. The disk can funnel gas, spiral arms can trigger density waves, and the gravitational potential is still organized in a way that favors disk-wide processes. In other words, the stage is still set, the actors are just missing. What these galaxies lack is fuel. But if that fuel were somehow restored through accretion, interaction, or even recooling of hot halo gas, it's plausible that star formation could restart. This isn't just speculation. There are observed galaxies that show signs of rejuvenation, where once quenched or quiescent systems begin to form stars again. These galaxies often reside in less dense environments, or on the outskirts of clusters, where gas from the intergalactic medium can still trickle in. One example is the class of galaxies known as blue sequence early types, which include S0s and anemic spirals that have acquired enough gas to light up their disks with modest new star formation. These galaxies blur the line between dying and dormant, much like anemics do, and they provide a real-world precedent for temporary quiet rather than permanent death. Moreover, in the cosmic web, galaxies are not closed systems. They exist in a network of filaments, nodes, and voids through which gas can flow over billions of years. Cold mode accretion, especially for smaller galaxies or those at the edges of clusters, can bring in new material long after the initial starburst phases have ended. If an anemic galaxy were to move into a region with available gas, or if gravitational instabilities allowed it to recapture expelled or halo gas, it could reignite its core processes. The process might not restore the galaxy to its former glory, the birth rate may never match the youthful heights of its spiral days, but even modest rejuvenation could create new stellar populations, reintroduce dust, and light up faint arms with glowing HI regions. The galaxy would no longer be anemic, but post-anemic, a phoenix-like system caught in a second wind. There's also evidence that minor mergers or interactions with gas-rich dwarf galaxies could deliver fresh fuel to otherwise passive disks. Such events are relatively common, and in a quiet galaxy, even a small supply of gas could make a visible difference. These minor interactions may explain some of the observed ultraviolet emission or low-level infrared flux in galaxies that are otherwise red and dead in the optical spectrum. Of course, not all anemic galaxies are candidates for revival. Many reside deep within dense cluster cores, where gas is scarce, stripped, or shock-heated beyond usability. In these environments, the pressure is too high, the intracluster medium too hot, and the galaxy's motion too violent to allow for gentle reaccretion or cooling. These anemics are more likely to be terminal cases, on their way to becoming S0s or faded shells of their former selves. The dormancy theory applies more strongly to peripheral galaxies, group members, or field spirals that have gone temporarily quiet. Simulations offer further nuance. Some show that galaxies can oscillate between active and passive states over cosmic timescales, depending on their gas supply and interaction history. These, flickering, galaxies might go through multiple cycles of star formation and quenching, especially in the early universe, but potentially even in the present-day cosmos. Anemic galaxies could be one of these in-between phases, paused but not broken, waiting for the universe to nudge them back into motion. Ultimately, whether an anemic galaxy is truly dying or merely dormant may depend on timing, environment, and chance. The distinction isn't always obvious from a snapshot in time, it's a matter of trajectory. Are we seeing the end of a long decline, or a lull in a longer, more dynamic life? In many ways, this is a question without a definitive answer. Even astronomers debate the criteria for what counts as quenched, semi-quenched, or temporarily quiet. But perhaps that's the beauty of anemic galaxies. They defy categorization. They sit between extremes, whispering not just of loss, but of possibility. Their faded light is not just a tombstone, it might also be a marker for rebirth, a dormant volcano, not extinct but sleeping. In the vast clockwork of the universe, where processes play out over billions of years, even a seemingly quiet galaxy might not be done with its story. It may just be resting before the next chapter begins. Galaxies, much like living organisms, have their own rhythms and metabolisms, ways in which they consume resources, convert them into energy, and evolve over time. This analogy helps us understand the pace at which a galaxy forms stars, uses up its gas, and transitions through different phases of activity and quiescence. In the cosmic ecosystem, galaxy metabolism is a crucial concept. Some galaxies are frenetic, rapidly converting gas into brilliant bursts of new stars. Others are languid, slowly burning their fuel over billions of years. Anemic galaxies occupy a unique niche within this spectrum. Their metabolism is markedly slow, a simmer rather than a blaze. At the core of galaxy metabolism is the star formation rate, SFR, the rate at which gas is transformed into stars, usually measured in solar masses per year. Active spirals like the Milky Way typically have SFRs of a few solar masses per year, with vigorous regions of star birth scattered along spiral arms. In contrast, starburst galaxies can form hundreds or thousands of solar masses worth of stars annually, lighting up the universe with their intense activity. Anemic galaxies, by comparison, have SFRs that are drastically lower than typical spirals of similar size and mass. The anemic label itself hints at this diminished vitality. Their gas reservoirs, both atomic and molecular, are depleted or severely reduced, constraining their ability to form new stars. As a result, their metabolism is in a state of decline, often many times slower than that of a healthy spiral. This slow metabolism manifests in several observable ways. For one, the specific star formation rate, SSFR, star formation rate normalized by stellar mass, is markedly lower in anemic galaxies. They are not only forming fewer stars, but forming them at a rate insufficient to maintain or grow their stellar population significantly. Instead, their total stellar mass remains largely constant, with only minor increments over time. This reduced metabolic pace also correlates with the galaxy's gas depletion time, the time it would take to use up the available gas at the current rate of star formation. In active spirals, depletion times tend to be on the order of a few billion years. In anemics, these times are often extended, as their star formation is so inefficient that remaining gas lingers in use, though, given the overall scarcity of gas, their total lifespan as star-forming systems is limited. Understanding why anemic galaxies have such slow metabolisms involves examining the interplay between gas availability, galactic dynamics, and external influences. Internally, gas densities may fall below the threshold needed to trigger gravitational collapse into molecular clouds. The stabilization of gas disks by the galaxy's rotation or dark matter halo can prevent gas from fragmenting and forming stars, further slowing metabolism. Externally, as we've discussed, environmental effects like ram pressure stripping and tidal harassment remove gas, effectively cutting off the fuel supply. Without fresh inflows, the galaxy's metabolism dwindles to a low hum. The interplay of these factors dictates where on the spectrum a galaxy's metabolism will lie. Anemic galaxies are therefore best described as having a metabolic rate characteristic of a slowly aging system, either bursting with new life nor completely extinguished. They embody a middle ground between vibrant spirals and passive lenticulars. This intermediate metabolic state means they can persist for billions of years in a semi-quiescent state, burning their remaining fuel at a glacial pace, slowly growing older without significant renewal. This slow metabolism also has consequences for the galaxy's structural evolution. Without robust star formation, the replenishment of young stars that maintain spiral arms fades. The disk's stellar population ages, and the contrast between arm and interarm regions diminishes, giving rise to the faint, ghostly spiral structure we associate with anemics. Thus, metabolism and morphology are deeply linked. The pace of resource consumption shapes the visible form of the galaxy. Moreover, this slow metabolic state impacts the galaxy's chemical evolution. With limited star formation, fewer supernovae enrich the interstellar medium with new metals, and the chemical composition becomes more static. This stasis is reflected in the relatively uniform, mature stellar populations and the declining abundance of elements critical for dust formation and molecular gas cooling. It's important to consider that the metabolic pace of a galaxy is not fixed. It can shift with changing conditions. Anemic galaxies may remain in this slow-burning phase indefinitely or transition into full quiescence if star formation ceases entirely. Conversely, as discussed earlier, some may briefly increase their metabolic rate through gas accretion or minor mergers, reigniting star formation. In the cosmic context, anemic galaxies are akin to middle-aged stars in a life cycle, burning their resources steadily but without the vigor of youth or the final decline of old age. Their metabolism is a key to understanding not just their current state but their potential futures and the broader tapestry of galaxy evolution. Even as anemic galaxies lose their youthful vigor and their star formation dwindles, their stellar and gaseous components often retain an echo of past vitality in the form of their kinematics, the internal motions that reveal how these galaxies rotate and evolve. The term, kinematic ghosts, aptly describes this phenomenon: galaxies that appear faded and quiet but whose stars and residual gas still carry the imprint of dynamic rotation, silently spinning through space like shadows of their former selves. In typical spiral galaxies, the rotation curve, the plot of rotational velocity versus distance from the galactic center, shows a well-organized pattern. The inner regions rotate more slowly, while the outer disk stars orbit at relatively constant, high velocities, a signature often used as evidence for dark matter halos. This ordered rotation supports the spiral structure, with density waves and gravitational perturbations shaping the arms and triggering star formation. For anemic galaxies, the big question is whether this organized rotation persists despite their fading star-forming activity. Observations and spectroscopic studies reveal that, indeed, many anemic galaxies retain a significant degree of rotation, with stellar disks that spin similarly to their active spiral cousins. The spiral arms may be faint and poorly defined, but the galaxy's stars continue their orbital dance, moving cohesively around the galactic center. This is particularly evident in studies using integral field spectroscopy, IFS, which allows astronomers to map the velocities of stars and gas across the face of the galaxy. These observations demonstrate that anemic galaxies often maintain disk-like kinematics, meaning their stars and any remaining gas rotate in relatively flat, orderly patterns rather than in random, chaotic motions. This rotational support differentiates them from elliptical galaxies, where stars exhibit more random velocities and the system behaves more like a three-dimensional stellar spheroid. However, the kinematics of anemic galaxies do show some subtle differences compared to healthy spirals. Their rotational velocities may be somewhat reduced, and the velocity dispersions, a measure of random stellar motions, can be elevated. This suggests that the stellar disks are dynamically hotter, possibly due to interactions, tidal stirring, or internal secular processes. These factors can puff up the disk, making it thicker and less orderly, which contributes to the faintness and fading of spiral structure. Gas kinematics tell a similar story. Though many anemic galaxies have lost much of their cold gas, the remaining gas often still follows the overall rotation of the stellar disk. In some cases, the gas may be confined to the central regions, showing signs of inflow or disturbed motions that hint at environmental influences like ram pressure stripping or tidal forces. The gas that remains can be kinematically decoupled from the stars in a few galaxies, possibly reflecting past mergers or accretion events, but overall, the gas preserves the rotation signature of the disk. The persistence of ordered rotation in anemic galaxies suggests that their structural framework remains intact, even as the processes that fueled their growth slow or stop. This supports the idea that they are transitional objects, not fully dead spheroids but faded disks caught between vitality and quiescence. Intriguingly, kinematic studies also reveal that some anemic galaxies show bar structures, elongated stellar features that can drive gas toward the center and influence star formation. These bars often remain active even in the anemic phase, indicating that internal dynamics continue to shape the galaxy's evolution, though the lack of gas limits their effectiveness in spawning new stars. On a broader scale, these kinematic signatures help astronomers reconstruct the evolutionary history of anemic galaxies. By comparing rotation curves and velocity dispersions with those of active spirals and lenticulars, researchers can estimate how much dynamical heating or stripping the galaxy has undergone. The kinematic ghost is thus a window into the galaxy's past encounters, environmental interactions, and internal transformations. Moreover, the continued rotation plays a vital role in maintaining the overall morphology of the galaxy. Without the angular momentum to support the disk, a galaxy would collapse into a more spheroidal shape. The fact that anemic galaxies still spin keeps their disks coherent, preserving the faint spiral patterns and preventing total morphological transformation. In conclusion, anemic galaxies, though faded and subdued in their star-forming activity, often continue to exhibit the quiet yet persistent rotation characteristic of healthy spirals. They are kinematic ghosts, dynamic memories of what they once were, spinning steadily through cosmic time. Their internal motions echo the fading light, a reminder that even in quietude, there is movement, structure, and life. One of the most intriguing and less visible players in the saga of anemic galaxies is the dark matter halo, a vast, invisible cocoon of mysterious matter that envelopes galaxies and profoundly influences their structure and evolution. Though we cannot see dark matter directly, its gravitational grip is crucial for holding galaxies together. In the case of anemic galaxies, whose gas reservoirs have been depleted and star formation slowed or halted, these dark matter halos might hold the key to preserving their faded disks and spiral structures, preventing them from collapsing or dispersing despite the loss of their gaseous lifeblood. To understand this, we first need to appreciate the role dark matter plays in galaxy formation generally. Galaxies form within massive halos of dark matter, which provide the gravitational well necessary to gather and hold baryonic matter, the normal matter that makes stars, gas, and dust. This invisible scaffold not only helps accumulate gas but also stabilizes the galaxy dynamically, influencing its rotation curve and preventing stars from flying apart due to their orbital velocities. In healthy spiral galaxies, the interplay between baryonic matter, stars and gas, and the dark matter halo creates a delicate balance. The halo's gravity supports the rotation of the disk, enabling the stars and gas to orbit in an orderly fashion, creating the well-defined spiral arms and star-forming regions. When the gas is abundant, it fuels new stars and shapes the galaxy's appearance. But what happens when the gas is stripped away or depleted, as in anemic galaxies? The stellar disk remains, but without the gas, the mass distribution changes. Gas often contributes a significant fraction of the baryonic mass, especially in the outer regions. Losing this component means the disk becomes less massive and less capable of self-gravity to maintain its structure. Intuitively, one might expect the disk to become unstable or even dissolve without gas. Here, the dark matter halo steps in as a cosmic stabilizer. Because the halo typically contains far more mass than the visible components, often 5 to 10 times the baryonic mass, its gravitational potential dominates the galaxy's dynamics. The halo's gravity helps to hold the stellar disk together, keeping it rotating and preventing the stars from dispersing, even in the absence of the gas that once fed star formation. Studies of anemic galaxies' rotation curves support this. Even with reduced gas content, many show rotation speeds consistent with massive, extended dark matter halos. This suggests that these halos have preserved the gravitational environment necessary for the disk to remain coherent. The disk may be fainter and less active, but it's still firmly anchored by the dark matter. The presence of a massive dark matter halo also has implications for the galaxy's resilience to environmental effects. While ram pressure stripping can sweep away gas, it cannot directly remove dark matter, which interacts only gravitationally. This means the stellar disk and halo remain gravitationally bound, even as the gas is lost. Consequently, anemic galaxies can maintain their disk morphology long after their gas has vanished. Another intriguing possibility is that the halo's gravitational influence helps to moderate internal dynamics, such as spiral density waves and bar instabilities, that might otherwise dissolve the disk structure over time. Even in the absence of ongoing star formation, the halo can stabilize the stellar orbits and preserve the overall morphology. Yet, the dark matter halo is not a static entity. Its mass distribution and shape can evolve, influenced by interactions, mergers, and accretion of material. In some scenarios, tidal forces within dense clusters can disrupt halos or strip their outer parts. However, the central regions, where the stellar disk resides, tend to be more robust. This helps explain why anemic galaxies, especially those in cluster outskirts or lower density environments, retain their disk structures despite environmental stresses. From a theoretical perspective, simulations incorporating dark matter dynamics reinforce this picture. Models show that galaxies with massive halos are more likely to survive gas depletion intact, maintaining their disks and spiral patterns longer than those with less massive halos. The halo acts as a protective shell, preserving the skeleton of the galaxy even as its flesh fades. This relationship also suggests that not all galaxies respond identically to gas loss. Those embedded in smaller or less massive dark matter halos may be more vulnerable to morphological transformation, evolving quickly into elliptical or spheroidal shapes after quenching. Anemic galaxies, with their preserved disks, may represent systems where the halo's mass and distribution favored disk survival. In sum, the dark matter halo mystery is central to understanding how anemic galaxies maintain their faint spiral forms and kinematic coherence despite a lack of the gaseous fuel that once animated them. It's a cosmic paradox. Invisible matter, unseen but omnipresent, is the unseen guardian that holds the fading lights together. Without these massive halos, anemic galaxies might simply dissolve into the cosmic night, losing not only their gas but their very shapes. This interplay between dark matter and baryonic matter in anemic galaxies highlights the complex, multi-component nature of galactic evolution, a dance between visible and invisible forces, between fading light and enduring gravity, shaping the universe in subtle but profound ways. Anemic galaxies occupy a curious middle ground in the cosmic family tree, nestled between the vibrant, star-forming spirals and the truly dead galaxies, ellipticals and lenticulars, S0s. Understanding what sets anemics apart from these fully passive systems not only illuminates their unique identity, but also reveals the pathways galaxies take as they evolve and age. First, consider the elliptical galaxies, often viewed as the archetype of galactic death. Ellipticals are characterized by their smooth, featureless light distributions and lack of cold gas and dust. They have little to no ongoing star formation, and their stellar populations are old, red, and metal-rich. The stars in ellipticals move in random orbits, creating a three-dimensional, spheroidal structure without a preferred rotation axis. Ellipticals often form through violent mergers, which scramble their internal motions and consume or expel gas, leaving behind a dynamically hot, gas-poor remnant. By contrast, anemic galaxies retain their spiral disk structure and ordered rotation. While their star formation is diminished, they are not devoid of gas entirely, nor are they dominated by random stellar motions. This key structural and kinematic difference means anemics still look like spirals, albeit faint and ghostly ones, whereas ellipticals are fundamentally different in shape and dynamics. The transition from spiral to elliptical generally requires more dramatic events, major mergers or collisions, that alter morphology and erase disks, processes not typically seen in anemics. Next, lenticular galaxies, or S0s, bridge the gap between spirals and ellipticals. They possess a prominent disk component like spirals but lack spiral arms and significant star formation. S0s often have older stellar populations, little gas, and a more subdued dust content. Their disks tend to be smoother and thicker, with less ongoing dynamical activity. S0s are common in dense cluster environments, and are often considered the end stage for galaxies that have lost their gas and stopped forming stars, but have not undergone the violent mergers that produce ellipticals. Anemic galaxies blur the line with S0s but differ in subtle yet meaningful ways. While anemics have faint spiral arms and sometimes residual star formation, S0s typically lack any spiral features and are more fully quiescent. Anemics are often viewed as transition objects, caught in the act of fading from spiral into lenticular morphology. They may eventually lose their spiral arms entirely, their disks becoming smoother and more S0-like as star formation ceases and stellar populations age. However, this evolution is gradual and can span billions of years. The presence of some gas and low-level star formation in anemics contrasts with the usually more gas-poor S0s. Even minimal gas content in anemics can fuel faint HI regions in UV emission, while many S0s are effectively dead in this regard. Moreover, anemic galaxies generally show more prominent dust lanes and less thickened disks than typical S0s, indicating less dynamical heating and less morphological transformation. Kinematically, anemics maintain faster, more disk-like rotation compared to the often dynamically hotter and thicker disks of S0s. This suggests that anemics still possess the internal conditions necessary for disk-supported structures, whereas S0s have undergone further dynamical evolution, possibly including minor mergers or tidal interactions that heat and thicken their disks. From a stellar population perspective, anemics usually exhibit a mix of aging stars with some intermediate-aged components, reflecting their slow star formation decline. S0s often host older, more homogeneous stellar populations with fewer young or intermediate stars, indicating a longer duration since active star formation ceased. The environments of these galaxy types also differ somewhat. Anemics are commonly found in intermediate density regions, such as the outskirts of clusters or groups, where environmental processes begin to act but are not yet dominant. S0s are more prevalent in cluster cores and dense environments, where gas removal and dynamical interactions are more intense, pushing galaxies toward full quiescence. In terms of evolutionary pathways, anemics can be seen as way stations on the road from active spirals to fully passive S0s. They embody the early to middle stages of gas depletion and star formation decline, preserving their spiral identity while quietly fading. Ellipticals, in contrast, generally represent a separate evolutionary route dominated by mergers and violent relaxation, often bypassing the anemic phase entirely. In summary, what sets anemic galaxies apart from truly dead galaxies like ellipticals and lenticulars is their retention of spiral structure, residual gas, faint but ongoing star formation, and disk-like kinematics. They are neither vibrant nor extinct but exist in a dimly lit intermediate state, where the light is fading but the form endures. This unique positioning makes them invaluable laboratories for studying galaxy transformation, the slow, complex processes that govern how galaxies age and die in the universe. Anemic galaxies are often considered prime candidates for being caught in transition, snapshots of spiral galaxies slowly evolving into lenticulars, or S0s, marking a crucial stage on the road to galactic senescence. This transitional hypothesis has gained substantial traction as astronomers seek to understand how the once vibrant, star-forming spirals become the quieter, more passive lenticular galaxies that populate dense environments like galaxy clusters. The key to this idea lies in observing the gradual fading and morphological changes that anemic galaxies display. Their spiral arms, though faint and poorly defined, are still present, unlike in fully developed S0s where the disk appears smooth and spiral structure is effectively erased. This suggests that anemics are in the early to intermediate phases of morphological transformation, retaining the skeleton of their former selves while slowly losing the features that once marked them as active spirals. One of the driving forces behind this transformation is the loss of cold gas, the essential fuel for star formation. As anemic galaxies lose their gas through environmental effects like ram pressure stripping and tidal interactions, the star formation rate drops. Without the birth of new stars, the bright blue populations that illuminate spiral arms dwindle, making the arms fade and the galaxy's overall color redden. This progression nudges the galaxy closer to the red, quiescent population characteristic of lenticulars. Additionally, the stellar disks of anemic galaxies may thicken over time due to gravitational perturbations, both internal, e.g., bars and spiral density waves weakening, and external, e.g., tidal harassment in clusters. A thickening disk has less contrast between arm and interarm regions, further smoothing out the morphology and making the spiral structure harder to discern. This structural evolution aligns closely with the observed characteristics of S0 galaxies. Kinematic studies support this evolutionary link. Anemic galaxies exhibit disk-like rotation but often show signs of increased velocity dispersion, indicating dynamical heating. Lenticulars tend to have thicker, more dynamically hot disks than spirals. The intermediate kinematic properties of anemics hint at ongoing processes that heat and stabilize the disk against fragmentation, consistent with a gradual transformation. Environmental context provides additional evidence. The majority of anemic galaxies are found in cluster outskirts, or group environments where environmental processes are strong enough to strip gas but not so overwhelming as to rapidly destroy disks. These are the regions where spirals may first begin to lose their gas and evolve morphologically before migrating further into the cluster core, where lenticulars dominate. This spatial distribution suggests a sequence of galaxy evolution tied to location, with anemics representing the transitional phase. However, this transformation is not guaranteed or uniform. The path from spiral to lenticular can depend on a galaxy's mass, orbit within the cluster, and history of interactions. Some anemic galaxies may never fully lose their spiral arms or may maintain low levels of star formation for extended periods, effectively stalling the transition. Others may experience minor mergers or gas accretion events that alter their evolutionary path. Simulations of galaxy clusters and groups often reproduce this transitional sequence. Spirals entering dense environments begin to lose gas, become anemic, and eventually settle as S0s, matching observed morphological fractions. These models show that the transition can take several billion years, emphasizing the slow, subtle nature of this galactic senescence. In this framework, anemic galaxies are more than faded spirals. They are waypoints in a dynamic evolutionary journey, representing the slow, steady dimming of galactic youth. Their existence offers a unique window into the mechanisms driving galaxy transformation and the interplay of internal processes and external forces. Ultimately, whether every anemic galaxy completes this transition or some remain in a prolonged intermediate state remains an open question. But the evidence positions them firmly as caught in transition, bridging the vibrant past of spiral galaxies and the quiescent future of lenticulars, embodying the universe's slow march toward galactic senescence. In the cosmic dance of galaxies, no system exists in true isolation. Many galaxies, including anemic ones, have companions, smaller satellite galaxies orbiting nearby, locked in a gravitational embrace. These satellites can play a pivotal role in shaping the fate of their host galaxies, sometimes robbing them of vital resources, sometimes feeding them fresh material. This relationship between satellites and their hosts is a subtle but powerful factor in the evolution of anemic galaxies, influencing their gas content, star formation activity, and overall vitality. The term, satellite starvation, captures one side of this interaction, the process by which satellites and companions effectively drain or prevent the inflow of gas that an anemic galaxy might otherwise capture and use for star formation. In galaxy groups and clusters, where anemics often reside, gravitational dynamics and the hot intracluster medium create an environment where gas reservoirs are limited and competition for resources is fierce. Satellites orbiting close to a larger galaxy can strip gas from the host or its surroundings through tidal forces and gravitational perturbations. While major mergers involve dramatic collisions, the cumulative effect of multiple minor interactions, or harassment, can gradually pull gas away from the primary galaxy's disk or halo. This stripping reduces the available fuel for star formation, deepening the anemic state. Moreover, satellites themselves consume gas in their own star formation, effectively locking up cold gas in smaller systems. Since gas is a finite resource in the local environment, this consumption can indirectly starve the host galaxy by limiting the shared gas pool. Another important factor is that satellites can influence the circumgalactic medium, CGM, the vast halo of gas surrounding galaxies. The CGM acts as a reservoir for future gas inflow, supplying material to replenish the galaxy's interstellar medium. Satellite interactions can disturb or deplete the CGM, preventing gas from cooling and accreting onto the host. This disruption further curtails star formation potential. However, the relationship isn't one-sided. Satellites can also act as sources of fresh gas and stars, potentially revitalizing anemic galaxies. When a satellite galaxy merges or is tidally disrupted, it can deliver cold gas and young stars into the host's disk, sparking localized bursts of star formation or adding complexity to the stellar population. These minor mergers or accretion events are generally less violent than major collisions, often leaving the host's disk intact while refreshing its material supply. For anemic galaxies on the brink of quiescence, such injections can be crucial, providing the fuel needed for a temporary revival of star formation. Observational evidence supports this dual role. Some anemic galaxies show signs of recent or ongoing interactions with satellites, including tidal streams, asymmetries in gas distribution, and localized star-forming regions associated with accreted material. These features highlight the importance of satellite interactions in shaping the late stages of galaxy evolution. The balance between satellite-induced starvation and feeding depends on several factors: the mass and orbit of the satellites, the density and temperature of the surrounding medium, and the host galaxy's own gravitational potential. In dense clusters, satellite stripping tends to dominate, pushing galaxies further toward gas depletion. In lower-density environments or groups, satellites may more often contribute gas and stars, aiding the host's vitality. In the broader cosmic ecosystem, satellite interactions are a key component of the galaxy life cycle, influencing how galaxies grow, evolve, and eventually fade. For anemic galaxies, these companions represent both a threat and a lifeline, potential thieves of gas and fuel, but also possible providers of renewal. Understanding satellite starvation and feeding helps us appreciate the nuanced and dynamic environment in which anemic galaxies exist. They are not merely isolated victims of cluster winds and ram pressure but active participants in a complex web of gravitational relationships that determine their fate. In contemplating the life of galaxies, a captivating analogy emerges. Like living beings or the Earth itself, galaxies might experience seasons, periodic phases of growth, dormancy, and renewal. This poetic concept of cosmic seasons invites us to consider whether anemic galaxies are simply experiencing a kind of winter in their long evolutionary cycles, a time of quiet hibernation rather than final death. Galaxies are complex, dynamic systems influenced by both internal processes and external forces. Their star formation rates, gas content, and structural characteristics fluctuate over timescales ranging from millions to billions of years. The notion that galaxies undergo cycles, periods of active star formation followed by quiescence, and potentially renewed activity, resonates with observations of diverse galactic populations across cosmic time. Anemic galaxies, with their suppressed but not extinguished star formation, diminished gas reservoirs, and faint spiral features, could be emblematic of a seasonal phase, a cosmic winter where the fires of star birth smolder low but haven't gone out entirely. During this time, the galaxy conserves its remaining resources, allowing its stellar populations to age and its morphology to fade, but not yet collapsing into complete passivity. This seasonal view is supported by several lines of evidence. First, ultraviolet and infrared observations reveal that anemic galaxies often harbor pockets of low-level star formation. This indicates they are not fully dormant, but in a subdued state where star formation persists sporadically or at low efficiency. Such flickering activity suggests a cyclical modulation of star formation, potentially triggered by the intermittent availability of gas or environmental interactions. Second, gas accretion and minor mergers can supply fresh fuel to galaxies, potentially reigniting star formation and shifting a galaxy from quiescence back to activity. This rejuvenation mimics the transition from winter to spring in galactic terms, a renewal phase where dormant systems reawaken. Observations of galaxies with post-starburst signatures or recent star formation bursts after quiescence reinforce this concept. Third, theoretical simulations model galaxies cycling between active and passive phases. They incorporate gas inflows, feedback from stars and black holes, and environmental effects, demonstrating that galaxies can experience multiple epochs of star formation separated by periods of low activity. Anemic galaxies fit naturally into these cycles as the phase characterized by slow metabolism and fading star formation. Importantly, this cyclical framework moves beyond a simplistic view of galaxy evolution as a one-way march from youth to death. Instead, it embraces the complexity of cosmic ecosystems where gas flows, environmental conditions, and internal dynamics interact to shape galaxies' lives over time. In this context, anemia is not a terminal illness but a seasonal state, a pause, a quiet interlude in the grand cosmic symphony. It reflects a phase where galaxies conserve energy, shed excess gas, and prepare for eventual rebirth or permanent quiescence depending on circumstances. Of course, not all galaxies may experience pronounced cycles. Some, especially those in harsh cluster cores, may face irreversible gas stripping and permanent quenching. But for many, especially those in intermediate density environments, seasonal cycling may be common. Viewing anemic galaxies as experiencing galactic winter enriches our understanding of their place in the universe. It highlights their potential resilience and the dynamic nature of galactic evolution. These quiet galaxies may simply be resting, awaiting the cosmic spring when fresh gas flows in, stars ignite anew, and the spiral arms regain their youthful brilliance. In the vast expanse of cosmic time, the notion of seasons reminds us that galaxies are not static monuments but living, evolving systems. Anemic galaxies whisper of cycles, of fading and flourishing, of quietude and renewal, echoing the rhythms of the universe itself. One of the quieter mysteries surrounding anemic galaxies lies not just in what we see, but in what we don't, their notable lack of strong radio emission. Unlike many star-forming spirals or active galaxies, anemics often exhibit what astronomers term radio silence. This absence or dramatic reduction of radio signals provides crucial clues about their physical state, particularly regarding their gas content and star-forming activity. Understanding why anemic galaxies are so quiet in radio wavelengths opens a window into the intimate relationship between hydrogen gas, star formation, and the life cycle of galaxies. Radio astronomy has long been a powerful tool for probing the cold, neutral hydrogen gas, HI, that pervades galaxies. Hydrogen emits radio waves at a characteristic wavelength of 21 centimeters, known as the HI line or 21 centimeters line. This emission arises from the hyperfine transition in neutral hydrogen atoms and is a fundamental tracer of the raw material needed for star formation. Mapping HI emission allows astronomers to estimate the amount, distribution, and dynamics of cold gas reservoirs in galaxies. In actively star-forming spiral galaxies, strong HI signals are often detected, highlighting abundant gas in their disks. This gas fuels the formation of molecular clouds and subsequent star formation. The 21 centimeters emission also traces large-scale structures like spiral arms, showing how gas flows and accumulates in regions conducive to stellar birth. Anemic galaxies, however, typically display significantly weaker or undetectable HI emission. Their radio silence in this regime is a direct consequence of their depleted gas reservoirs. As we've seen, environmental effects such as ram pressure stripping in clusters can remove neutral hydrogen from the galactic disk, pushing the galaxy toward an anemic state. Without sufficient HI, the characteristic 21 centimeter signals vanish or become too faint to detect with current instruments. This lack of neutral hydrogen has profound implications. It not only halts the formation of molecular gas clouds but also disrupts the ongoing cycle of star birth. Without cold gas, the galaxy's star formation engine stalls, leading to a gradual fading of the young, blue stellar populations that dominate active spirals. Beyond the HI line, anemic galaxies also tend to lack other forms of radio emission commonly associated with star-forming regions and active galactic nuclei, AGN. For example, synchrotron radiation, produced when cosmic ray electrons spiral in magnetic fields, is often strong in galaxies with active star formation or AGN activity. This emission is typically correlated with supernova remnants and energetic processes linked to young massive stars. In anemic galaxies, the diminished star formation means fewer massive stars and consequently fewer supernova explosions. The cosmic ray population dwindles, reducing synchrotron emission. Likewise, if the galaxy lacks an active central black hole, or if the AGN is weak or dormant, radio emission from the nucleus is minimal or absent. Thus, the combined lack of HI and synchrotron radio emission results in the radio quietness observed in anemic galaxies. This absence is a telling signature of their quiescent nature and gas-poor state. However, the picture is not uniform. Some anemic galaxies exhibit faint or patchy radio emission, often localized to residual star-forming regions or the central core. These weak signals hint at lingering pockets of activity, where enough gas remains to sustain minor star formation or where weak AGN activity might persist. Such cases provide important contrasts that help astronomers understand the gradual transition from activity to quiescence. Radio observations have also played a role in studying the environmental impact on anemic galaxies. By comparing HI maps of galaxies inside clusters with those in the field, astronomers have directly visualized the ram pressure stripping process, where gas is physically removed from the galaxy by the intra-cluster medium's pressure. These studies reveal truncated or displaced HI disks in anemic galaxies, often with gas tails trailing behind, indicating ongoing or recent stripping events. Furthermore, radio continuum studies help trace magnetic field structures and cosmic ray populations, offering insights into the internal dynamics and past star formation histories of these galaxies. The lack of strong radio emission underscores the faded dynamism within anemic disks, reinforcing their classification as transitional or fading systems. The radio silence of anemic galaxies also aids in differentiating them from other galaxy types in multi-wavelength surveys. While active spirals and starbursts shine brightly across the radio spectrum, and ellipticals may show radio-loud AGN, anemics stand out for their subdued radio profiles. This characteristic serves as a diagnostic tool in large-scale galaxy evolution studies. On a broader scale, the radio quietness of anemic galaxies ties into the theme of galaxy quenching and environmental influence. It reflects a stage where the galaxy's fuel for star formation is exhausted or forcibly removed, and energetic feedback processes have subsided. The radio silence becomes a hallmark of this advanced evolutionary stage. As radio astronomy advances with new facilities like the Square Kilometre Array, SKA, and Next Generation Very Large Array, INGVLA, astronomers expect to detect even fainter HI and continuum emission from anemic galaxies. These future observations promise to refine our understanding of gas depletion timescales, residual star formation, and the detailed mechanisms that shut down galactic engines. In summary, the rare radio signals from anemic galaxies stem directly from their lack of neutral hydrogen and reduced star formation activity. This, radio silence, is both a symptom and a signature of their fading state, offering vital clues about their current condition and evolutionary trajectory. By listening to the absence of radio waves, astronomers decode the quiet stories of galaxies transitioning from vibrant youth to silent maturity, deepening our grasp of the complex life cycle of galaxies in the universe. Ultraviolet UV astronomy has opened a revealing window into the otherwise faint and subdued worlds of anemic galaxies. Though these galaxies are characterized by their diminished star formation and faded spiral arms, UV observations frequently uncover hidden pockets of low-level star formation, demonstrating that beneath their quiet appearances, there can still be faint flickers of life. Unlike optical wavelengths, which are dominated by the light of older, cooler stars, ultraviolet light is primarily emitted by young, massive stars with short lifespans, typically less than a few 100 million years. This makes UV an extremely sensitive tracer of recent star formation, capable of detecting activity that might be too weak or too patchy to stand out in other bands. Many studies using space telescopes equipped with UV detectors, such as the Galaxy Evolution Explorer, GALEX, have revealed that while anemic galaxies lack the widespread, vigorous star formation typical of healthy spirals, they often show localized UV emission in their disks. These UV-bright regions correspond to sites where gas remains dense enough to collapse and form new stars, even if only at a trickle compared to their former rates. This low-level star formation often concentrates in the inner regions of anemic galaxies, where residual gas tends to accumulate due to gravitational potential wells and sometimes the influence of bars or spiral density waves. The UV emission may also appear in faint outer rings or spiral arm fragments, hinting at complex, non-uniform gas distributions shaped by environmental factors and internal dynamics. One key insight from UV observations is that anemic galaxies are not necessarily completely dead, but rather in a quiescent or dormant state where star formation persists at a significantly reduced level. This nuanced understanding challenges earlier assumptions that the fading spiral arms and red colors implied total cessation of star birth. UV data also provides clues about the timescales of star formation decline. The presence of young stars in anemic galaxies indicates that star formation ceased gradually, over hundreds of millions to a few billion years, rather than abruptly. This gradual quenching aligns with environmental mechanisms like ram pressure stripping, which remove gas over extended periods, rather than violent mergers that shut down star formation rapidly. Moreover, UV observations help identify rejuvenation events, small bursts of star formation triggered by gas accretion, minor mergers, or tidal interactions. Such episodes may temporarily brighten portions of anemic galaxies, contributing to their complex evolutionary paths. Detecting UV bright knots in otherwise faint disks supports the idea that anemic galaxies can experience intermittent periods of renewed activity, albeit at low intensity. Another important role of UV astronomy is in disentangling age and metallicity effects that influence galaxy colors. Optical and near-infrared colors can be reddened either by aging stellar populations or by dust extinction, making it difficult to determine the true star formation history. UV light, being sensitive to recent star formation and less affected by older stars, helps break this degeneracy. The spectral energy distributions, SEDs, of anemic galaxies, combining UV, optical, and infrared data, reveal a mix of older stars dominating the light at longer wavelengths and a minor but measurable contribution from young stars in the UV. This dual population indicates a slow decline rather than an abrupt stop in star formation. UV studies also tie into the role of environmental quenching. Anemic galaxies in cluster outskirts or groups often show more UV emission than those in dense cores, consistent with the idea that gas removal processes are more gradual or incomplete farther from the cluster center. The spatial distribution of UV emission can trace where gas survives longest or where recent accretion might have occurred. Furthermore, UV imaging allows for detailed mapping of star formation rates, SFRs, across anemic galaxies, uncovering subtle gradients and asymmetries. These patterns reflect how environmental effects, like ram pressure or tidal forces, unevenly strip gas, influencing where stars continue to form. Such spatially resolved data provide a richer picture of how star formation tapers off regionally within these galaxies. In addition to star formation, UV observations can detect emission from evolved stars like hot horizontal branch stars and post-asymptotic giant branch, post-AGB, stars, which contribute to the UV light in older populations. However, the presence of localized, not UV sources in anemics generally points toward ongoing star formation rather than purely old stellar components. Taken together, these UV clues paint a picture of anemic galaxies as systems in a delicate balance. They are neither vibrant spirals blazing with young stars nor fully passive, gas-per lenticulars or ellipticals. Instead, they harbor the faint embers of star formation, flickering quietly within a galaxy whose overall activity is steadily waning. This residual star formation may last for billions of years, allowing anemic galaxies to persist as intermediate evolutionary stages or even to revive temporarily under the right circumstances. The UV light they emit is a testament to their resilience, suggesting that galaxies do not simply die, but often fade gradually, with life flickering beneath the surface. In essence, ultraviolet observations provide one of the most sensitive and revealing probes into the subtle ongoing processes within anemic galaxies. They confirm that these galaxies are not silent tombs but are better understood as cosmic retirees, aged and slowed, but still capable of sparking new light in a universe that continues to evolve. The study of anemic galaxies, with their distinctive properties and subtle transitions, has greatly benefited from the insights provided by modern galaxy evolution simulations. These computational models allow astronomers to explore the physical processes driving galaxy transformation over billions of years, testing hypotheses that observations alone cannot fully resolve. By simulating different environments, gas dynamics, star formation, and gravitational interactions, researchers can recreate the conditions under which anemic galaxies form, evolve, and sometimes fade away. At the heart of many galaxy evolution simulations is the interplay between baryonic matter, stars, gas, and dust, and dark matter halos, which provide the gravitational framework. These models incorporate complex physics, including hydrodynamics, radiative cooling, feedback from supernovae and active galactic nuclei, AGN, and environmental effects like ram pressure stripping and tidal interactions. This multiphysics approach is crucial for reproducing the diverse morphological and kinematic features observed in real galaxies, including the elusive anemic class. One of the key findings from simulations is the role of environmental mechanisms in driving the evolution toward an anemic state. Models of galaxy clusters and groups demonstrate that as spiral galaxies enter dense environments, they experience ram pressure stripping from the hot intracluster medium. Simulations show how the galaxy's cold gas is gradually pushed out of the disk, starting from the outskirts and progressing inward. This gas loss leads to a progressive reduction in star formation, causing the galaxy to fade and its spiral arms to become less pronounced, hallmarks of anemic galaxies. Simulations also reveal that tidal harassment and gravitational encounters with other galaxies contribute to gas removal and morphological transformation. Repeated high-speed flybys in clusters can heat the stellar disk, thicken it, and distort spiral patterns. These cumulative effects, modeled in cosmological simulations, produce galaxies that retain faint disks and spiral arms but have significantly diminished gas and star formation, matching the observed properties of anemics. Furthermore, advanced simulations incorporating feedback processes from supernovae and AGN help explain how internal mechanisms regulate star formation during the anemic phase. Energy and momentum injected into the interstellar medium can prevent gas from cooling and collapsing, further suppressing star formation. Feedback can also drive gas outflows, accelerating the depletion of fuel for new stars. Simulations have also been crucial in understanding the timescales involved in the anemic phase. Models consistently find that the transition from a gas-rich, actively star-forming spiral to an anemic galaxy occurs over several hundred million to a few billion years, depending on environmental conditions and galaxy mass. This slow progression aligns with observational constraints, reinforcing the view of anemics as intermediate stages rather than instantaneous transformations. Another intriguing insight from simulations is the impact of galaxy mass and orbit within clusters. More massive galaxies tend to retain gas longer due to deeper gravitational wells, potentially prolonging the anemic phase. Conversely, low-mass spirals are stripped more quickly, evolving more rapidly toward lenticular or elliptical morphologies. The galaxy's orbit, whether it plunges through the cluster core or skirts the outskirts, also determines the strength and timing of stripping processes. Cosmological hydrodynamical simulations, such as those from the Illustris, Eagle, and TNG projects, include large samples of galaxies evolving in realistic environments. These simulations have successfully produced populations of galaxies with anemic-like properties, faded spirals with reduced gas and star formation, embedded naturally within the hierarchical growth of cosmic structures. By comparing simulated galaxy catalogs with observations, researchers have identified the typical environmental histories and evolutionary tracks leading to anemic stages. Simulations also explore the possibility of rejuvenation events, brief periods of renewed star formation triggered by gas accretion or minor mergers during or after the anemic phase. These events add complexity to the simple fade-to-death scenario and help explain why some anemic galaxies retain patches of star formation and UV emission. Moreover, simulation studies have begun to probe the detailed kinematic signatures of anemic galaxies. By tracking the motion of stars and gas, models show how disk rotation can persist despite gas depletion, while velocity dispersions increase due to environmental heating. These kinematic properties are consistent with observational findings and support the classification of anemics as intermediate systems retaining spiral disk dynamics. Importantly, simulations highlight that anemic galaxies are not an isolated or static class but part of a continuum of galaxy evolution influenced by a spectrum of processes acting over cosmic time. They demonstrate how subtle balances between gas inflow, star formation, environmental stripping, and feedback shape galaxies' journeys from active youth through anemic middle age and ultimately to quiescent old age. In conclusion, galaxy evolution simulations provide vital context and mechanistic understanding for the anemic galaxy phenomenon. They reveal how environmental pressures and internal feedback combine to slowly extinguish star formation, sculpt morphology, and produce the faint, ghostly spirals we observe. These virtual laboratories allow astronomers to test and refine theories, bridging the gap between snapshots captured by telescopes and the dynamic, unfolding story of galaxies in our universe. Not every galaxy burns bright. Some whisper through the void, quietly aging, patiently waiting, or perhaps slowly dying in a universe that never truly stops moving. This evocative truth encapsulates the subtle beauty and profound mystery of anemic galaxies, those faint, faded spirals whose delicate light traces a cosmic narrative of transformation, endurance, and impermanence. Throughout this long exploration, we have peeled back the layers of what it means to be an anemic galaxy, a system caught in a liminal state between vibrant youth and silent old age. They are neither the dazzling star factories of active spirals nor the cold, passive behemoths of elliptical and lenticular galaxies. Instead, anemics exist in a twilight realm, their spiral arms whispering the ghostly echoes of past vigor, their stellar populations aging quietly under a fading glow. Their subdued star formation, sparse gas reservoirs, and environmental scars tell stories of slow decline and external influence. The stripping winds of galaxy clusters, the gravitational tugs of neighboring companions, and the exhaustion of their internal fuel tanks combine to slow the galactic engines, dimming the fires of starbirth. Yet, these galaxies are not merely dying. Many hold on to fragile embers of activity, flickers of ultraviolet light revealing that some stars still ignite, that some gas still collapses, and that some hope for renewal lingers. The cycles of cosmic seasons suggest that anemic galaxies might not be frozen in their decline but could one day revive, stirred by new gas flows or gentle encounters. Their radio silence speaks volumes, and their faint spiral patterns challenge our understanding of galactic morphology and evolution. Simulations reaffirm that they are dynamic actors in the cosmic play, caught in the delicate balance of internal processes and external pressures, evolving over billions of years. The study of anemic galaxies offers a humbling reflection on the nature of change in the universe. Just as stars are born, age, and die, so too do galaxies live their own life cycles, shaped by forces both within and without. Anemic galaxies are the universe's quiet elders, holding memories of brighter days while facing the inevitability of fading light. In the vastness of space and time, they remind us that cosmic evolution is not always dramatic or explosive. Sometimes it is a slow whisper, a gradual dimming, a patient fading, processes that demand patience and subtlety to observe and understand. As astronomers continue to unlock their secrets through observations across the electromagnetic spectrum and increasingly sophisticated simulations, anemic galaxies will remain essential keys to unraveling the full story of how galaxies grow, change, and eventually fade away. So when you gaze up at the night sky, remember that beyond the bright stars and brilliant galaxies lie those quiet, anemic spirals, gently aging in the cosmic ocean, their fading light a testament to the universe's ceaseless flow, its endless cycles of birth, life, and quiet decline. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.